Okay, now that we've covered a little bit of background on what machine learning is and some of the major types of machine learning problems, there's nothing like getting started with our own machine learning application in Python. And we're going to get started on that right now. So to do that, we're going to make use of several important Python libraries that will support our work. These include scikit-learn, scipy, numpy, pandas, and matplotlib. We recommend installing all of these using the Anaconda Python distribution, since it comes with all the libraries we'll need in this part of the course. If you have some other existing Python installation, you can install the libraries we'll be using from the command line using pip. The most important library we'll be using for machine learning is called scikit-learn. Scikit-learn is the most widely used Python library for machine learning, and it will be the basis for this course. It's an open source project that's under continual development and improvement, and supports a very wide array of important machine learning algorithms. It has excellent online documentation and a very active user community. Because of this broad adoption, scikit-learn has many sample applications, tutorials, and code examples that are available online. So one valuable reference that we recommend you use while you take this course is the scikit-learn user guide and the API documentation, which contains further details on the different algorithms that are in the library, along with details on the various options that these algorithms support. Scikit-learn makes use of two other Python scientific computing libraries called scipy and numpy. Scipy is a Python library that supports data manipulation and analysis methods that are commonly used in scientific computing. So this includes support for statistical distributions, optimization of functions, linear algebra, and a variety of specialized mathematical functions. In some parts of this course, we'll make use of scipy's ability to provide what are called sparse matrices, which are a way to store large tables that contain mostly zeros. So more on that later. NumPy is a Python library for scientific computing that contains support for some fundamental data structures used by scikit-learn, such as multidimensional arrays. Typically, data that's input to scikit-learn will be in the form of a NumPy array. Pandas is a Python library for data manipulation and analysis. And if you took course 1 in this series, you've already had experience with what pandas can do. The key data structure pandas supports that we'll be using is called a data frame, which is basically like a spreadsheet table with rows and named columns. So unlike the arrays supported by NumPy, the columns in a data frame can be of all different types. You can have one column holding string values, another column holding a date, another column holding a floating point number, and so on. Pandas also has great support for reading and writing data in a variety of formats, everything from comma-separated CSV files to SQL, the structured query language used by databases, and more. Matplotlib is a widely used Python 2D plotting library that produces high-quality figures in a variety of formats and interactive environments across platforms. Matplotlib can be used in Python scripts, the Python and IPython shell, web application servers, and a variety of different graphical user interface toolkits. If you've taken course 2 in this data science series, you'll already have some experience with using Matplotlib. Here we'll primarily be using matplotlib.pyplot for data analysis, since it can create histograms, bar charts, error charts, scatter plots, and so forth with just a few lines of code. Here are the versions of the main libraries used in this course. Please make sure the versions of scikit-learn and other libraries you're using are the same or greater than what's listed here. If you're not sure which versions you have, here's some example code that shows you how you can check which versions of scikit-learn, numpy, and pandas you have. You can use similar code to check the versions of other libraries. Okay, now that we've covered a little bit of background on what machine learning is and some of the major types of machine learning problems, there's nothing like getting started with our own machine learning application in Python. And we're going to get started on that right now. So to do that, we're going to make use of several important Python libraries that will support our work. These include scikit-learn, SciPy, NumPy, Pandas, and Matplotlib. We recommend installing all of these using the Anaconda Python distribution, since it comes with all the libraries we'll need in this part of the course. If you have some other existing Python installation, you can install the libraries we'll be using from the command line using pip. The most important library we'll be using for machine learning is called scikit-learn. Scikit-learn is the most widely used Python library for machine learning, and it will be the basis for this course. It's an open source project that's under continual development and improvement, and supports a very wide array of important machine learning algorithms. It has excellent online documentation and a very active user community. Because of this broad adoption, scikit-learn has many sample applications, tutorials, and code examples that are available online. So one valuable reference that we recommend you use while you take this course is the scikit-learn user guide and the API documentation, which contains further details on the different algorithms that are in the library, along with details on the various options that these algorithms support. Scikit-learn makes use of two other Python scientific computing libraries called SciPy and NumPy. SciPy is a Python library that supports data manipulation and analysis methods that are commonly used in scientific computing. So this includes support for statistical distributions, optimization of functions, linear algebra, and a variety of specialized mathematical functions. In some parts of this course, we'll make use of SciPy's ability to provide what are called sparse matrices, which are a way to store large tables that contain mostly zeros. So more on that later. NumPy is a Python library for scientific computing that contains support for some fundamental data structures used by scikit-learn, such as multidimensional arrays. Typically, data that's input to scikit-learn will be in the form of a NumPy array. Pandas is a Python library for data manipulation and analysis. And if you took course 1 in this series, you've already had experience with what Pandas can do. The key data structure Pandas supports that we'll be using is called a data frame, which is basically like a spreadsheet table with rows and named columns. So unlike the arrays supported by NumPy, the columns in a data frame can be of all different types. You can have one column holding string values, another column holding a date, another column holding a floating point number, and so on. Pandas also has great support for reading and writing data in a variety of formats, everything from comma-separated CSV files to SQL, the structured query language used by databases, and more. Matplotlib is a widely used Python 2D plotting library that produces high-quality figures in a variety of formats and interactive environments across platforms. Matplotlib can be used in Python scripts, the Python and IPython shell, web application servers, and a variety of different graphical user interface toolkits. If you've taken course 2 in this data science series, you'll already have some experience with using Matplotlib. Here we'll primarily be using matplotlib.pyplot for data analysis, since it can create histograms, bar charts, error charts, scatter plots, and so forth with just a few lines of code. Here are the versions of the main libraries used in this course. Please make sure the versions of scikit-learn and other libraries you're using are the same or greater than what's listed here. If you're not sure which versions you have, here's some example code that shows you how you can check which versions of scikit-learn, NumPy, and Pandas you have. You can use similar code to check the versions of other libraries. For our first machine learning exploration, we're going to build an extremely simple form of object recognition system. Now, although the example we'll use is very simple, it does reflect many of the same key machine learning concepts that go into building real-world commercial systems. The dataset we're going to use is a small, very simple example dataset derived from one originally created by Dr. Ian Murray at the University of Edinburgh for the task of training a classifier to distinguish between different types of fruit. So to create the original data set, Dr. Murray went to a nearby store, bought a few dozen oranges, lemons, and apples of different varieties, and recorded their measurements in a table. So he sat down and he looked at the height and the width, estimated their mass, and so forth. So we've reformatted his original data slightly and added one or two extra simulated features, such as a color score, for instructional purposes. This data set is called Fruit Data with Colors.txt, and it's included in the folder of materials that you downloaded for this course. Now, you might think that fruit prediction is a sort of silly and impractical scenario, and given the limited nature of this data set, it is a bit of a toy example, but actually, food companies do indeed now rely on machine learning systems that aren't all that different in concept from the ones we're about to build. So they can do automated quality control. And in fact, there do exist, for example, real systems used by fruit shipping companies that screen for rotten oranges during processing. Now, the features that they use in building these systems are a little more sophisticated than the ones we'll look at here. So, for example, quality control systems for rotten orange detection use ultraviolet light that can detect interior decay, which is often less visible than just by looking on the surface. Anyway, to solve machine learning problems, you can think of the input data as a table where each object, so in our case a piece of fruit, is represented by a row, and the attributes of the object, the measurement, the color, the size, and so forth, in our case for a piece of fruit, the features of the fruit are represented by the values that you see across the columns. In a supervised learning problem, the data set will also typically contain a special column with the label of the object if the data set does not have such a field already. Sometimes you can derive it from information that's in one or more columns. So to make sure you're ready to continue, make sure you've run the following code snippet that loads the proper libraries we're going to need to proceed. And we'll show those here now. So the first thing we're going to do is to load the fruit dataset file using the very handy read table command in pandas. Now this will read the dataset from disk and store it into a data frame variable that we'll call fruits here. Okay, let's look at this dataset and dump out the first few rows of the data frame. So here we can see that each row of the data set represents one piece of fruit as represented by several features that are in the table's columns. So in order, the columns that we see are fruit label. So this is the training label that we'll use. It's a number that corresponds to the general type of fruit. So for example, 1 is an apple, 2 is a mandarin orange, 3 is a regular orange, and so forth. So this label was supplied by the human creator of the data set. The fruit name and fruit subtype columns contain text descriptions of the general and specific fruit categories. And the fruit name corresponds, it's a text form of the corresponding fruit label in the same row. Now, we won't be using these name columns as features. I've just included them here to make the data set a bit more readable for our purposes. After that, the features in this representation include measurements for each fruit that capture its mass in grams and its width and height in centimeters. And finally, there's a feature stored in a column called color score that's meant to be a single number that captures a rough idea of the color of the fruit. So in a real system, this would actually be something more sophisticated, like a histogram of the distribution of colors, or maybe the pixels from an actual image or video of the fruit. But for our purposes, we're going to just summarize the color along a spectrum scale. That'll be a handy summary that we can use that will just be easy to visualize. So scores close to 1 mean the fruit is red. Scores around 0.7 indicate yellow, and so forth. So looking at this data frame, we can see that it contains 59 rows corresponding to 59 different pieces of fruit that have been measured and entered into the table. So our goal here is to build a classifier from this data that can predict the correct type of fruit for any given observation of features, such as mass, height, width, and color score. So for example, can we tell, based on the color score and the dimensions, the difference between an orange and a lemon, and have the classifier predict the type of piece of fruit correctly, just from its observed measurements. Now, assuming for the moment that we already had a classifier ready to go, how would we know if its predictions were likely to be accurate? Well, we could choose a fruit sample called a test sample for which we already had a label. So we could feed the features of that piece of fruit into the classifier and then compare the label that the classifier predicts with the actual true label of the fruit type. So here's a very important point, though. If we use one of our labeled fruit examples in the data that we use to train the classifier, we can't also use that same fruit sample later as a test sample to also evaluate the classifier. Why is that? Well, a key ability that our classifier needs to have is that it needs to work well on any input sample, any new pieces of fruit that we might see in the future, not just on the ones that we have in our training set. Because our classifier could simply memorize every sample in the training set, it'd be pretty trivial to just give back the correct label for any one of the same samples later, right? So measuring the classifier's performance later using the same samples that we've used to train it in the first place doesn't tell us anything about how well the classifier is likely to work for fruit that we haven't seen before. It will only tell us what we already know about what's in the training set. So since our only source of labeled data is the data set we've been given, to estimate how well the classifier will do on future samples, what we'll do is split the original data set into two parts. We'll have an array of labeled samples called the training set that will be used to train the classifier, and then we'll hold out the remaining labeled samples and put them into a second separate array called the test set that will be used to then evaluate the trained classifier. So to create training and test sets from an input data set, scikit-learn provides a handy function that will do this split for us, called, not surprisingly, train test split. And here's an example of how we'll use it. This function randomly shuffles the data set and splits off a certain percentage of the input samples for use as a training set, and then puts the remaining samples into a different variable for use as a test set. So in this example, we're using a 75-25% split of training versus test data. And that's a pretty standard relative split that's used. It's a good rule of thumb to use in deciding what proportion of training versus test might be helpful. As a reminder, when we're using scikit-learn, we'll denote the data that we have using different flavors of the variable x, capital X, which is typically a two-dimensional array or data frame. And the notation we'll use for the labels will be typically based on lowercase y, which is usually a one-dimensional array or a scalar. Now, note the use of the random state parameter in the train test split function. So this random state parameter provides a seed value to the function's internal random number generator. If we choose different values for that seed value, that will result in different randomized splits for training and test. So if we want to get the same training and test split each time, we just make sure to pass in the same value of the random state parameter. And so here we're going to set that parameter to 0 for all our examples. The training test split function will put the training set here into xtrain, the test set into xtest, the training labels into ytrain, and the test labels into ytest. So this is a 75-25 partitioning of the original data into these two parts. And this is the variable naming convention we'll use for pretty much all of our coding. We'll put the rows of the data without the label, the training instances, into this capital X variable, and the list of corresponding labels for those rows into a variable called lowercase y. When using the training set and a test set, we'll then use xtrain that holds the training instances to train the classifier, and xtest to evaluate the classifier after it's been trained. And we're going to show a short snippet of code here now that illustrates how to do that. So here we can see the results of the function, applying this train test split function. You can see that it has indeed split our fruit data set into training and test sets with the correct proportion of samples. Now that we have a training and a test set, we're ready for the next step. And we'll look now into more depth at the data itself before we proceed with giving it to a machine learning algorithm. In general, if you're thinking about applying machine learning to a data set, it's a really good first step to actually look at the data set first, maybe using some simple visualization methods, or even simply scrolling through to look at the various values in the different rows before proceeding. And there are several reasons for doing this. First, it's helpful to simply get a sense for what's actually in the data set, because it may be that in inspecting the features of each object, you might get a better idea of what type of cleaning or pre-processing still needs to be done to the data, and of the range of values or the distribution of values that is typical for each attribute or each feature. This initial exploration can be especially valuable when you're dealing with complex objects like text that may be represented by many features that are extracted using a series of several pre-processing steps. For example, you might discover that the data set you got has a single column with a person's name that still needs to be split into two separate first and last name columns. As for example, if you're using the name as one of the prediction features, that might be important. Second, you might notice missing or noisy data, or maybe some specific inconsistencies, such as the wrong data type being used for a column, incorrect or inconsistent units of measurement for a particular column, a particular feature. Or maybe you'll notice that there aren't enough examples of a particular labeled class. You might notice, for example, that some measurements of a person's weight, if let's say you're doing a health application with a patient record for each row, some might accidentally have the weight in grams instead of kilograms and so forth. And that can make obviously a huge difference in how accurate your results are. So inspecting and visualizing the data will help you detect and understand these potential sources of noise or errors. And finally, it might turn out that for your data set, your problem is actually solvable without machine learning. Now, this doesn't happen all that often, but if it does, you can save yourself considerable time by simply looking at what data exists in your data set. So in one scenario, your data set might actually contain a feature that is clearly a strong indicator of the label that you want to predict. For example, if your goal was to predict whether a house's location was in New York City versus San Francisco based on attributes like its sales price, its elevation above sea level, how big its rooms are, and so forth. It could be that your data set might also include, let's say, a URL to a photo of the house, and that image might, contain, GPS coordinates to the house within its metadata, or maybe the URL encodes location in a slightly non-obvious but human recognizable way that you can pick out, and you've solved your problem just by looking at the data. So As I said, this scenario isn't all that common, but it does happen. And so a brief check of your data set could save you a lot of unnecessary work. Okay, so we'll make sure we've got a training set from our original data set unit using train test split. And we'll do all our initial visualization and feature analysis on this training set. And we're only going to use the test set for actually evaluating the classifier once it's trained. This complete separation of training and test sets is very important, and we'll go into more depth later about some specific reasons why it's important in later class. So now that we have a training set selected, let's create some simple visualizations to look at how the features of the objects in the training set, in our case, different fruits, relate to each other and to the labels. So with these visualizations, we get at least two major benefits. First, we can get an idea of the range of values that each feature takes on, and we can immediately see any unusual outliers that are very different from other points, and that might indicate noise or a missing feature or other problem with the data set. And second, we may be able to get a better idea of how likely it is that a machine learning algorithm could do well at predicting the different classes by seeing how well clustered and well separated the different types of objects are in feature space. So feature space refers to the representation of an object using specific features that are in certain columns of the data that we have. So for example, if the features for objects with the same label, for example, all the lemons, have similar feature values, we should see a well-defined cluster appear in the visualization. While if the features for objects that have different labels tend to be quite different, we should see these well separated into visibly different areas of the plot. So having objects whose classes are well defined and well separated in feature space is a good indication that suggests the classifier is likely to be able to predict the class label from the features with good accuracy. Now, the visualization techniques that I'll be showing here work well when you have a relatively small number of features, let's say less than 20. Later, when we cover unsupervised learning, you'll learn how to create visualizations of data sets that use a very large number of feature dimensions, so hundreds or even thousands or millions, to represent each object. But for now, the first visualization tool we'll use is called a feature pair plot, and that's shown here. So this plot shows all possible pairs of features and produces a scatter plot for each pair, showing how the features are correlated with each other or not. Each point in the scatter plot represents a piece of fruit, colored according to the class it belongs to, and positioned using the pair of features assigned to that scatter plot. Along the diagonal is a histogram showing the distribution of feature values for that feature. So in this pair plot, the dimensions shown here in order are the height, width, mass, and color score of the fruit examples in our training set. So the upper left corner of the histogram here shows the distribution of the height feature for all samples in the training set. And the scatter plot to its immediate right plots the width of each sample on the x-axis and the height of the sample on the y-axis. Now, just by looking at this pair plot, we can already see that some pairs of features, like the height and color score in the top right corner here, are good for separating out different classes of fruit. And this suggests that a classifier that was trained using those features could likely learn to classify the various fruit types reasonably well. Here's the code that we'll use to create this plot, and let's run this now on our training set. Note that a pair plot like this does not show interactions between all features that might exist, just between pairs of them. So the plot itself may not show all the interesting relationships that do exist between the features. But it does give you a rough idea of some of the interactions that might exist. We can also look at feature spaces that use a subset of three features by creating a three-dimensional plot. And here's the code that we can use to do this. So in this example, we plot different fruits using 3 coordinates. So here we'll show the width, the height, and the color score. Here again, each point represents a single piece of fruit and it's colored according to its fruit label value. So in this 3D plot, you can actually rotate the plot along the various axes by holding down the mouse button and then dragging. And you can clearly see that the different fruit types are in pretty well-defined clusters that are also well separated in feature space. So now that we've taken a look at the data, next we'll look at a simple prediction task for this data set in a bit more detail. Now that we've gotten a sense for what's in our data set, as a simple example to get started, we're going to use this data set to train a classifier that will automatically identify any future pieces of fruit that might come our way, based on the features available to the classifier, such as the object's color, size, and mass. To do this, we'll use a popular and easy-to-understand type of machine learning algorithm known as k-nearest neighbors, or KNN. The k-nearest neighbors algorithm can be used for classification and regression, though here we'll focus for the time being on using it for classification. KNN classifiers are an example of what's called instance-based or memory-based supervised learning. What this means is that instance-based learning methods work by memorizing the labeled examples they see in the training set, and then they use those memorized examples to classify new objects later. The K in KNN refers to the number of nearest neighbors the classifier will retrieve and use in order to make its prediction. In particular, the KNN algorithm has 3 steps that can be specified. First of all, when given a new, previously unseen instance of something to classify, a KNN classifier will look into its set of memorized training examples to find the K examples that have the closest features. And we'll talk about what closest means in a minute. Second, the classifier will look up the class labels for those k-nearest neighbor examples. And then once it's done that, it will combine the labels of those examples to make a prediction for the label of the new object, typically, for example, by using simple majority vote. Let's look at a visual example of a KNN classifier that's based on our fruit data set. So what I've done here is taken our training set and plotted each piece of fruit using 2 of its features, the width and the height. These 2 features together form what is called the feature space of the classifier. And I've shown each data point's label using the colors shown in the legend. So as you can see, there are 4 different colors here that correspond to the 4 types of fruit that are in our data set. These broad areas of color show how any point given width and height could be classified according to a 1 nearest neighbor rule. So in other words, I've set k equal to 1 here. So for example, a data point over here that had a height of 6 centimeters and a width of 9 centimeters would be classified as an apple because it falls within this red area here that the KNN classifier has decided map to objects that are apples based on the dimensions. Or for example, if the classifier saw a piece of fruit that had a height of 4 centimeters and a width of 7 centimeters, it would be classified as a mandarin orange because it falls within this decision area that's assigned to mandarin oranges. So what does it mean to have a 1 nearest neighbor rule? Where did it come up with these different class assignments in the first place? Well, let's take a look at the apple example over here. The object that has a height of 6 centimeters and a width of 9 centimeters, if you give the classifier that point, what it will do is search within all the different training examples that it's seen. So it will look at all these points and see which one is closest. So we're looking at the nearest single neighbor. So we're looking at k equals 1. We're trying to find the 1 point that's closest to our what's called the query point. This is the point we want to classify. So in this case, we can see probably that this point over here is the nearest neighbor of the query point in feature space. Similarly, if we look at the Mandarin example over here, the closest training set object to the query point is one of these, probably maybe this point right here. Okay, so that's the nearest neighbor of that query point. So for any query point in the feature space, let's say we're over here in the lemon zone. The nearest neighbor to this query point would be this training set point right here. And because the training set points are labeled, we have the labels for those. In the one nearest neighbor case, the classifier will simply assign to the query point the class of the nearest neighbor object. So because the nearest neighbor here is an apple, the query point here will get classified as an apple. And if we look at the Mandarin orange point over here, the nearest data point is the Mandarin orange, so it will get classified in that region. And if we do that for every possible query point, we get this pattern of class regions. The zones where we transition from one class to another, this line right here is called the decision boundary, because query points that are on one side of the line get mapped to one class, and points that are on the other side of the line get mapped to a different class. So I want to note that in this example, we've been finding nearest neighbors using an ordinary Euclidean distance function that gives both features equal weight. We could instead use what's called a weighted Euclidean distance function that gives different features different weights in the distance calculation, which might improve the accuracy in some applications. Using a weighted distance function can change the behavior of the classifier significantly, and here's an example of what I mean. So on the left, we have our standard setup, the Euclidean distance with equal feature weights for both the height and the width features. On the right, I've changed the distance function to give the width feature, the y-axis measurement, 10 times the weight of the height feature. So I haven't changed the training data. You can see all the training points are still in the same positions. What we've changed is the distance definition between the points. A small change in the width feature now has a much larger effect on the classification decision than it did before, because of that 10 times multiplier factor when the distance is computed. And you can see that on the right, this results in decision boundaries and regions that are now quite skewed and sort of compressed in the y direction compared to the original Euclidean distance with equal feature weight. Whether or not this is the effect you want will depend on your specific application. Some of the facts I've mentioned about KNN using ordinary Euclidean distance may also change if you change to a weighted Euclidean distance measure. For example, using a weighted distance measure, the decision boundaries between classes can change significantly. They may no longer lie along equidistant lines perpendicular to the line joining training points of different classes. So I'll show you what I mean. In the original Euclidean distance with equal weights on the features, when we had decision boundaries between points of different classes, we could draw a line through these 2 points, and then the decision boundary would be equidistant, perpendicular to the line joining these 2 points. You can see that happens here and here in these examples. But once we switch to a weighted Euclidean distance, like you can see that the decision boundary here is no longer perpendicular to the line bisecting these 2 points of different classes. It's now sort of skewed. So this is one example of how certain facts might change with weighted Euclidean distance. On a related note, KNN can be sensitive to features that have values on very different scales. If that's the case with your data, you should consider normalizing the training data before fitting the classifier. to ensure that all features are on the same scale. We'll cover how to do that to normalize your data in week 2 as part of the module on regression. So because this is a k nearest neighbor classifier, and we're looking at the case where k equals 1, we can see that the class, the boundaries here, the decision boundaries, let's take an example over here. We have a point over here that's an orange, another point that's a lemon here, and we can see the decision boundary, because it's based on Euclidean distance and we're weighting points equally, that the decision boundary goes exactly at a distance equidistant to these two things. It's exactly halfway between these 2 points, right? Because if it were any closer to this point, it would be mapped to the orange class, and if it were any closer to the lemon instance over here, it will be mapped to the lemon class. So you can see this pattern for all the decision boundaries here. This line is equidistant to these 2 nearest points. So this is basically how the k nearest neighbor classifies new instances. So you can imagine with points, query points where k is larger than 1, we might use a slightly more complicated decision rule. Let's take this example over here. Suppose we have a query point that's an orange, and we're doing 2 nearest neighbor classification. So in that case, the 2 nearest points are these 2 points here. And in cases where k is bigger than 1, we use a simple majority vote. We take the class that's most predominant in the labels of the neighbor examples. So in this case, the labels happen to agree. They're both oranges, and so this point in a 2 nearest neighbor situation would be classified as an orange. When you get points that are closer to, say, a point over here, the 2 nearest neighbors in that case might be these points here, in which case you could choose randomly between them to break the tie. Typically, the value of k is odd, so that we can simply, in k equals 3, it might look like this. And so you can see that the 3 nearest neighbors here are a red point, an apple, a blue point, an orange, and another red point, an apple. So in the k equals 3 case, the vote would go towards labeling this as an apple. And that's basically all there is to the basic mechanism for KNN classifiers. More generally, to use a nearest neighbor algorithm, we specify 4 things. First, we need to define what distance means in our feature space, so we know how to properly select the nearby neighbors. In the example that I just showed you with the fruit data set, we use the simple straight line or Euclidean distance to measure the distance between points. Second, we must tell the algorithm how many of these nearest neighbors to use in making a prediction. This must be a number that is at least 1. Third, we may want to give some neighbors more influence on the outcome. For example, we may decide that neighbors that are closer to the new instance that we're trying to classify should have more influence or more votes on the final label. Finally, once we have the labels of the k nearby points, we must specify how to combine them to produce a final prediction. Here's a specific example of some typical choices we might make for these 4 things. The most common distance metric, and the one that scikit-learn uses by default, is the Euclidean or straight line distance. So technically, if you're interested, the Euclidean metric is actually a special case of a more general metric called the Minkowski metric, where there's a parameter p that's set to 2 that will give you the Euclidean metric. And you'll see this in the notebook when you look at the actual settings. They're done in terms of the Minkowski metric. We might choose to use the 5 nearest neighbors, let's say, for our choice of k. And we might specify that there's no special treatment for neighbors that are closer. So we have a uniform weighting. Also, by default, scikit-learn will apply for the 4th criterion a simple majority vote, and it'll predict the class with the most representatives among the nearest neighbors. We'll look at a number of alternative classifiers in next week's class on supervised learning methods. For now, let's take a look at the notebook to see how we apply a k-nearest neighbor classifier in Python to our example fruit dataset. As a reminder, you can use Shift-Tab to show the documentation pop-up for the method as you're entering it to help remind you of the different parameter options and syntax. So recall that our task was to correctly classify new incoming objects, in our example case, pieces of fruit. So our newly trained classifier will take a data instance as input and give us a predicted label as output. The first step in Python that we need to take is to load the necessary modules, as well as load the dataset into a pandas data frame. After we've done that, we can dump out the first few rows using the head method to check the column names and get some examples of the first few instances. Now, what I'm doing next here in the notebook is defining a dictionary that takes a numeric fruit label as the input key and returns a value that's a string with the name of the fruit. And this dictionary just makes it easier to convert the output of a classifier prediction to something a person can more easily interpret, the name of the fruit in this case. So for this example, we'll define a variable capital X that holds the features of our data set without the label. And here I'm going to use the mass, width, and height of the fruit as features. So this collection of features is called the feature space. We define a second variable, lowercase y, to hold the corresponding labels for the instances in X. Now we can pass X and Y to the train test split function in scikit-learn. Normally the splitting into training and test sets is done randomly, but for this lecture I want to make sure we all get the same result, so I set the random state parameter to a specific value. In this case I happen to choose 0. The results of the train test split function are put into the 4 variables you see on the left, and these are marked as xtrain, xtest, ytrain, and ytest. We're going to be using this x and y variable naming convention throughout the course to refer to data and labels. Once we have our train test split, we then need to create an instance of the classifier object, in this case a KNN classifier, and then set the important parameter, in this case the number of neighbors, to a specific value to be used by the classifier. We then train the classifier by passing in the training set data in xtrain and the labels in ytrain to the classifier's fit method. Now the KNN classifier that I'm using in this case is an example of a more general class called an estimator in scikit-learn. So all estimators have a fit method that takes the training data and then changes the state of the classifier or estimator object to essentially enable prediction once the training is finished. In other words, it updates the state of the KNN variable here, which means that in the case of k-nearest neighbors, it will memorize the training set examples in some kind of internal storage for future use. And that's really all there is to training the KNN classifier. And the first thing we can do with this newly trained classifier is to see how accurate it's likely to be on some new, previously unseen instances. To do this, we can apply the classifier to all the instances in the test set that we've put aside, since these test instances were not explicitly included in the classifier's training. One simple way to assess if the classifier is likely to be good at predicting the label of future previously unseen data instances is to compute the classifier's accuracy on the test set data items. Remember that the KNN classifier did not see any of the fruits in the test set during the training phase. So to do this, we use the score method for the classifier object. So this will take the test set points as input and compute the accuracy. And now the accuracy is defined as the fraction of test set items whose true label was correctly predicted by the classifier. We can also use our new classifier to classify individual instances of fruit. In fact, this was our goal in the first place, was to be able to take individual instances of objects and assign them a label. So here, for example, I'll enter the mass, width, and height for a hypothetical piece of fruit that is fairly small. And if we ask the classifier to predict the label using the predict method, we can see the output is that it predicts it's a mandarin orange. I can then pass a different example, which is maybe a larger, slightly elongated fruit that has a height that's greater than the width and a larger mass. In this case, using the predict method on this instance results in a label that says the classifier thinks this object is a lemon. Now let's use a utility function called plot fruit KNN that's included in the shared utilities module that comes with this course. This will produce the colored plots I showed you earlier that have the decision boundaries. You can then try out different values of k for yourself to see what the effect is on the decision boundaries. The uniform parameter that I pass in here as the last parameter is the weighting method to be used. So here I'm passing in the string uniform, which means to treat all neighbors equally when combining their labels. If you like, you can try changing this to the word distance if you want to try a distance-weighted method. You can also pass your own function, but we'll leave that for later. We can also see how our new classifier behaves for different values of k. So in this series of plots, we can see the different decision boundaries that are produced as k is varied from 1 to 5 to 10. We can see that when k has a small value like 1, the classifier is good at learning the classes for individual points in the training set, but with a decision boundary that's fragmented with considerable variation. This is because when k equals 1, the prediction is sensitive to noise, outliers, mislabeled data, and other sources of variation in individual data points. For larger values of k, the areas assigned to different classes are smoother and not as fragmented, and more robust to noise in the individual points, but possibly with some mistakes, more mistakes in individual points. This is an example of what's known as a bias-variance trade-off, and we'll look at that phenomenon and its implications in more depth in next week's class. Given the changes in the classifier's decision boundaries we observe when we change k, a natural question might be how the value of k, how the choice of k, affects the accuracy of the classifier. We can plot the accuracy as a function of k very easily using this short snippet of code. We see that, indeed, larger values of k do lead to worse accuracy for this particular dataset and fixed single train test split. Keep in mind, though, these results are only for this particular training test split. To get a more reliable estimate of likely future accuracy for a particular value of k, we would want to look at results over multiple possible train test splits. We'll go into this issue of model selection next week as well. In general, the best choice of the value of k, that is, the one that leads to the highest accuracy, can vary greatly depending on the data set. In general, with k nearest neighbors, using a larger k suppresses the effects of noisy individual labels, but results in classification boundaries that are less detailed. So we've taken several steps in this course so far. We've looked at a data set, plotted some features. We then took the features and learned how to compute a train test split, use that to train a classifier, and use the resulting classifier to make some predictions for new objects. So congratulations, you've just created and run your first machine learning application in Python. In next week's class, we'll go into some supervised learning methods in more depth and look beyond k nearest neighbors to learn how and why to apply other types of classifiers to machine learning problems. When we build a supervised learning model, whether it's for classification or regression, it's not only important for the model to make correct predictions on the examples it saw in the training data, If that were the only definition of success, then supervised learning algorithms could simply memorize all of the training data and always have 100% accuracy. Of course, that's not what happens in the real world. What we actually want from a supervised machine learning algorithm is the ability to predict a class or target value correctly on a test set of future examples that haven't been seen before. This ability to perform well on a held-out test set is the algorithm's ability to generalize. How do we know that our trained supervised model will generalize well? In other words, perform well on an unseen test set. Well, typically, machine learning makes an important assumption that the future test set has the same properties, or more technically, is drawn from the same underlying distribution as the training set. This means that if we observe our model has good accuracy on the training set, and the training set and test sets are similar, we can also expect that it will do well on the test set. Unfortunately, sometimes this doesn't happen due to an important problem known as overfitting. Informally, overfitting typically occurs when we try to fit a complex model with an inadequate amount of training data. An overfitted model uses its ability to capture complex patterns by being great at predicting lots and lots of specific data samples or areas of local variation in the training set, but it often misses seeing global patterns in the training set that would help it generalize well on the unseen test set. It can't see these more global patterns because, intuitively, there's not enough data to constrain the model to respect these global trends. As a result, the training set accuracy is a hopelessly optimistic indicator for the likely test set accuracy if the model is overfitting. Understanding, detecting, and avoiding overfitting is perhaps the most important aspect of applying supervised machine learning algorithms that you should master. There are serious real-world consequences to overfitting. The reading for this week contains one example from the medical world you might find interesting. To understand the phenomenon of overfitting better, let's look at a few visual examples. The first example that we'll look at for overfitting involves regression. In this chart, on the x-axis, we have a single input variable that might be, for example, the size of a piece of property, and we have a target variable on the y-axis. For example, this might be the market selling price of a house that sits on that piece of property. So in regression, we're looking to find the relationship between the input variable and the target variable. And we start off with the idea of a model that we want to fit that might explain this relationship. So one example of a model that we could try to fit would be a linear model. So trying to predict that there's a linear relationship between the input variable and the target variable. So the regression model might fit a straight line to these points. In this case, the model has underfit the data. The model is too simple for the actual trends that are present in the data. It doesn't even do well on the training points. So these blue points would represent the training points, the input to the training process for the regression. And when we underfit, we have a model that's too simple, doesn't even do well on the training data, and thus is not at all likely to generalize well to test data. On the other hand, if we pick a better model, for example, the idea that this might be a quadratic relationship, we might actually be able to apply that and get what looks like a much better fit. So this would be an example of a reasonably good model fit. We've captured both the general trend of the points while also ignoring the little variations that might exist due to noise. The third example might be, we might hypothesize that the relationship between the input variable and the target variable is a function of several different parameters. Let's say a polynomial, so something that's very bumpy. If we tried to fit a more complex model to this set of training data, we might end up with something that looks like this. So this more complex model has more parameters, so it's able to capture more subtle behavior, but there's also much higher variance here, as you can see. So it's more focused on capturing the more local variations in the training data rather than trying to find the more global trend that we can see as humans in the data. So this is an example of overfitting. In this case, there's not enough data to really constrain the parameters of the model enough so that it can recognize the global trend. This second example will look at overfitting in classification. So this diagram shows a simple two-dimensional classification problem where each data instance is represented by a point and where there are two features associated with each data instance. This is a binary classification problem, so points are labeled either red over here or blue. And the problem in classification is to find a decision boundary. So as we saw with k nearest neighbors, we want to take this feature space and find regions that are associated with the different labels. So one type of classifier that we'll look at shortly is called a linear classifier, where we try to find a decision boundary that's essentially a straight line through the space. So just as in regression, we can have underfitting models, good fitting models, and overfitting models. So an example of an underfitting model would be something that really didn't look much at the data, maybe something like this, that only looked at one feature, for example. So again, this is an overly simplistic model. It doesn't even capture the patterns, the division between the classes in the training data well, and so it would be unlikely to generalize. So this is an underfitting model. A reasonably good model that fits well would be a linear model that finds this general difference between the positive class over here and the negative class over here. So you can see that it's aware of this sort of global pattern of having most of the blue negative points in the upper left and most of the red positive points more toward the lower right. And it's robust enough in the sense that it ignores the fact that there may be occasionally a blue point in the red region or a red point in the blue region. Instead, it's found this sort of more global separation between these two classes. So this is a reasonably well-fitting model. An overfitting model, on the other hand, would typically be a model that has lots of parameters so it can capture complex behavior. And so it would try to find something very clever where it tried to completely separate the red points from the blue points in a way that resulted in a highly variable decision boundary. So this has the advantage that, a questionable advantage, that it does capture the training data classes very well. It predicts the training data classes almost perfectly. But as you can see, if the actual division between the classes is captured by this linear model, the overfit model is going to make lots of mistakes in the regions where it's trying to be too perfect in some sense. So you'll see this typically with overfitting. The overfit model is highly variable. And again, it's trying to capture too many of the local fluctuations and does not have enough data to see the global trend that would result in better overall generalization performance on new unseen data. This third example shows the effect of modifying the k parameter in the k nearest neighbors classifier that we saw previously. The three plots shown here show the decision boundaries for k equals 10, k equals 5, and k equals 1. And here we're using the fruit data set again with the height of a piece of fruit on the x-axis and the width on the y-axis. So the k equals 10 case, as you recall, k equals 10 means that for each query point that we want to get a prediction for, let's say over here, we have to look at the 10 nearest points to the query point. And we'll take those, we won't go through all 10 here, but let's just say there are several here that are nearby and we'll average or combine their votes to predict the label for this point. So in the k equals 10 case, we need the votes from 10 different data instances in the training set to make our prediction. And as we reduce k, so when k equals 5, we only need 5 neighbors to make a prediction. So for example, if the query point was here, we'd look at these 4 and then possibly whatever was the closest in this set. Let's say that one or this one. And then finally in the k equals 1 case, that's the most unstable in the sense that for any query point we only look at the single nearest neighbor to that point. And so the effect of reducing k in the k nearest neighbors classifier is to increase the variance of the decision boundaries, because the decision boundary can be affected by outliers. If there's a point far away, it has much greater effect on the decision boundary in the k equals 1 case than it would in the k equals 10 case when the votes of 9 other neighbors are also needed. And so you can see that by adjusting the value of k for the k nearest neighbors classifier, we can control, in some sense, the degree of model fitting that's appropriate for a data set. Now, the actual value of k that works best can only be determined by evaluating on a test set. But the general idea is that as we decrease k for k-NN classifiers, we increase the risk of overfitting because, for the reason I mentioned before, where at k equals 1, for example, we're trying to capture very local changes in the decision boundary that may not lead to good generalization behavior for future data. To explore different supervised learning algorithms, we're going to use a combination of small synthetic or artificial data sets as examples, together with some larger real-world data sets. scikit-learn has a variety of methods in the sklearn datasets library to create synthetic datasets. The synthetic dataset we'll use for illustration purposes are typically low-dimensional examples, because they only use a small number of features, typically 1 or 2. This makes them easy to explain and visualize. Many real-world datasets, on the other hand, have a higher dimensional feature space. In other words, they have dozens, hundreds, or even thousands or millions of features. So some of the intuition we gain from looking at low-dimensional examples doesn't always translate to high-dimensional datasets, and we'll discuss that a bit more later. For example, high-dimensional datasets, in some sense, have most of their data in corners with lots of empty space, and that's kind of difficult to visualize. We'll go through some examples later in the course. But the low-dimensional examples are still useful so that we can understand things like how a model's complexity changes with changes in some key parameters. So for basic regression, we'll start with a simple problem that has one informative input variable, one noisy linear output, and 100 data samples. Here's a plot of a data set using a scatter plot with each point represented by one dot. The x-axis shows the feature value, and the y-axis shows the regression target. To create this, we use the makeRegression function in sklearn datasets. Here's the code in the notebook. To illustrate binary classification, we'll include a simple 2-class dataset with 2 informative features. Here's a scatter plot showing each data instance as a dot with the first feature value corresponding to the x-axis and the second feature value corresponding to the y-axis. The color of a point shows which class that data instance is labeled. I'm calling this data set simple because it has only 2 features, both of which are informative. In this case, these 2 classes are approximately linearly separable, which means that a basic linear classifier placed between them does a pretty good job at discriminating the points in the 2 classes. So turning to the notebook, to create this data set, we used the makeClassification function in sklearn datasets, creating 100 points that roughly group the data samples into one cluster per class, with here a 10% chance of randomly flipping the correct label of any point, just to make it a little more challenging for the classifier. We'll also look at a more complex binary classification problem that uses two features, but where the two classes are not really linearly separable, instead forming into various clusters in different parts of the feature space. This dataset was created in two steps. First, using the make_blobs function in sklearn datasets to randomly generate 100 samples in 8 different clusters, and then by changing the cluster label assigned by make_blobs, which is a number from 1 to 8, to a binary label by converting it using a modulo 2 function, assigning the even index points to class 0 and odd index points to class 1. To illustrate multi-class classification, we'll use our familiar fruits dataset, which, as you may remember, has 4 features and 4 possible target labels. Here on the left, I'm showing the array of scatter plots that we saw in week 1 that shows the relationship between all possible pairs of features and the class labels, with the distribution of values for each feature along the diagonal. To illustrate a real-world regression problem, we'll use a dataset derived from the Communities and Crime dataset in the UCI repository. Our dataset uses a subset of the original features and target values, which were originally created from combining several U.S. government data sources, like the U.S. Census. Each data instance corresponds to a particular geographic area, typically a town or region of a city. Our version of this dataset has 88 features that encode various demographic and socioeconomic properties of each location, with 1,994 location data instances. The target value that we'll try to predict is the per capita violent crime rate. To use this dataset, we use the load crime dataset function that's included with the shared utilities module for this course. Let's revisit the first example of machine learning we encountered in week 1, k-nearest neighbors models. Those are a good starting point to continue our exploration of supervised learning because they're simple to understand and can be used for both classification and regression. Let's recall that for classification, the k-nearest neighbor classifier simply memorizes the entire training set, and then to classify a new instance does 3 steps. First, it finds the k-nearest most similar instances to the new instance in the training set. Then it gets the labels of those training instances, and then it predicts the label of the new instance as a function of the nearby training labels, typically by a simple majority vote. Here's how a k-nearest neighbor classifier using only one nearest neighbor, that is with k equal to 1, makes its predictions for the simple binary synthetic dataset. So as you might recall from week 1, where we applied a nearest neighbors classifier to our multi-class fruit dataset, here we're applying the nearest neighbors classifier to our simple binary classification problem, where the points in class 0 are labeled with yellow dots, and the points in class 1 are labeled with black dots. And just as we did for the week 1 problem with fruit classification, here we're also showing how the entire feature space is broken up into different decision regions according to the predictions that the k-nearest neighbors classifier would make at each point in the decision space. So for example, a point out here in the yellow region represents a point that the classifier would classify as class 0, and a point, let's say over here, the classifier would classify as class 1. So because this is a one nearest neighbors classifier, to make a classification prediction for any given query point, the classifier simply looks back into its training set. So these points here represent all the points in the training set. So for any given point, let's say here, the classifier will simply find the training point that's closest, namely this one, and assign the predicted class to simply the class of the nearest point in the training set. Likewise, if we have a point over here, the nearest point in the training set is actually this point right here that has a class 0 label, and so that point would get assigned a class 0. And in fact, this whole region right here represents all the points that are closer to the class 0 training point than any of the other class 1 training points. So this whole region here represents a 1 nearest neighbor's prediction of class 0. So the k nearest neighbors classifier with k equal to 1, you can see that the decision boundaries that derive from that prediction are quite jagged and have high variance. And this is an example of a classification model that has high model complexity. And in fact, you can see that the 1 nearest neighbors classifier is overfitting the training data in this case. It's trying to get correct predictions for every single training point while ignoring the general this trend between the two classes, namely that most of the yellow points are in this side of the feature space and most of the black points are in this side. So the 1 nearest neighbors classifier can be said to be overfitting in this case. And here's what happens when we increase k from 1 to 11. Now the classifier must combine the votes of the 11 nearest points, not just 1. So single training data points no longer have as dramatic an influence on the prediction. The result is a much smoother decision boundary, which represents a model with lower model complexity, where the decision boundary has much less variance. Actually, if we increased k even higher to be the total number of points in the training set, the result would be a single decision region where all predictions would be the most frequent class in the training data. And as we saw for the fruit data set, k nearest neighbors classifiers can be applied to any number of classes, not just 2. The code for this example in the notebook uses a special function in the shared utilities library for this course called plot toClass KNN. If you run this code and compare the resulting training and test scores for k equals 1, 3, and 11, which are shown in the title of each plot, you can see the effect of model complexity on a model's ability to generalize. In the k equals 1 case, the training score is a perfect 1.0, but the test score is only 0.80. As k increases to 3, the training score drops to 0.88, but the test score rises slightly to 0.88, indicating the model is generalizing better to new data. When k equals 11, the training score drops a bit further to 0.81, but the test score is even better at 0.92, indicating that this simple model is much more effective at ignoring minor variations in the training data and instead capturing the more important global trend in where the classes tend to be located, with the best overall generalization performance as a result. The nearest neighbors approach isn't useful just for classification. You can use it for regression too. So here are 3 plots that show the same simple regression problem with one input feature and the corresponding target values in the training data. The leftmost plot here, this one, shows just the original training data points. And the middle and right plots show the predictions made by a KNN regression algorithm when k equals 1 and k equals 3. So in these plots, you can see the training points are actually in green. These green circles are the training points. And the blue triangles are the output of the k nearest neighbor regression for any given input value of x. So for example, the KNN regression prediction for this point here is this y value here. So how did the nearest neighbors regressor compute these values? Well, it did it in a similar way to what we saw for classification. So for example, if the query point we're interested in is predicting the value associated with this x value, we simply find the training point that has the x value that's closest to this query point. So in this case, that would be this training point. And because this is a 1 nearest neighbor problem, we simply take the target value associated with this training point and use that as the output, the target for the query point. Similarly, if this were the query point here, then the nearest neighbor in the training set would be this point here. And so the output prediction for this particular x value will be the target value of the nearest neighbor, or this value that's just above 100. And so if we do that for all these different x values, we'll get these different predictions using the one nearest neighbor approach. Similarly, if we look at the k equals 3 case, where we look at 3 nearest neighbors, let's take this example here of negative 1.25, let's say. Well, what are the 3 training points that have x values closest to negative 1.25? They would be this training point, that training point, and this training point. Now, with regression, what we do is instead of taking a majority vote, we don't have class values here as targets, we have continuous values. So we can average these 3 target values. And if we do that, we find that the output when the query point is this x value is going to be the average of the y values of the 3 nearest training points, or this value here. Similarly, if we have a query point that is here, then the 3 nearest neighbor points are here, here, and here. And the average target value of these 3 training points is something like this. Here's the corresponding code in the notebook that produced these regression plots. These use the k-neighbors regressor class, which, like the classification case, takes the n-neighbors setting as a key parameter. Because the target values in a regression problem are continuous, as compared to the discrete values that we see for classifier target labels, to assess how well a regression model fits the data, we use a regression score called R-squared that's between 0 and 1. We'll cover some additional types of regression evaluation scores later in the course. For the R-squared value, a value of 1 corresponds to the best possible performance, a model that makes perfect predictions. A value of 0 corresponds to a model that makes a constant value prediction that's always just the mean value of all the training target values. The R-squared value is sometimes known as the coefficient of determination. Just as we did for classification, let's look at the connection between model complexity and generalization ability as measured by the R-squared training and test values on this simple regression dataset. This series of plots in the notebook shows how the KNN regression algorithm fits the data for k equals 1, 3, 7, 15, and in an extreme case of k equals 55 that represents almost half the training points. We can see the same pattern in model complexity for KNN regression that we saw for KNN classification, namely that small values of k give models with higher complexity, and large values of k result in simpler models with lower complexity. Starting on the left, when k equals 1, the regression model fits the training data perfectly with an R-squared score of 1.0. But it's very bad at predicting the target values for new data samples, as reflected in the R-squared test score of only 0.155. As the value of k increases, which we can see acts to smooth out these local variations to capture more of the global trend, again the training set score drops, but the model gets better at generalizing to new data, and the test score goes up as k increases. Finally, in this series, the model with k equals 15 has the best test set performance, with an R-squared score of 0.485. Increasing k much further, however, to k equals 55 results in both the training and test set scores dropping back down to lower levels, as the model now starts to underfit. In other words, it's too simple to do well even on the training data. The pros of the nearest neighbor approach are that it's simple and easy to understand why a particular prediction is made. A k-nearest neighbor approach can be a reasonable baseline against which you can compare the performance of more sophisticated methods. When the training data has many instances, or each instance has lots of features, this can really slow down the performance of a k-nearest neighbors model. So in general, if your data set has hundreds or thousands of features, you should consider alternatives to k-nearest neighbors models, especially if your data is sparse, meaning that each instance has lots of features, but most of them are 0. So to sum up, and as a review of what we saw in week 1, the two key parameters for both regression and classification in nearest neighbors models are naturally n neighbors, which controls the value of the number of neighbors to consider, and thus the model complexity, as we saw, and the metric parameter, which controls the distance function between points, and thus which points are considered as nearest when finding neighbors. We didn't explore the metric parameter here, and that's beyond the scope of this course, but in most cases, the default Euclidean setting works pretty well with most data sets. One of the simplest kinds of supervised models are linear models. A linear model expresses the target output value in terms of a sum of weighted input variables. For example, our goal may be to predict the market value of a house, its expected sales price in the next month, for example. Suppose we're given two input variables, how much tax the property is assessed each year by the local government, and the age of the house in years. You could imagine that these two features of the house would each have some information that's helpful in predicting the market price, because in most places there's a positive correlation between the tax assessment on a house and its market value. Indeed, the tax assessment is often partly based on market prices from previous years, and maybe a negative correlation between its age in years and the market value, so older houses may need more repair and upgrading, for example. One linear model, which I've made up as an example, could compute the expected market price in US dollars by starting with a constant term, here 212,000, and then adding some number, let's say 109 times the value of tax paid last year, and then subtracting 2,000 times the age of the house in years. So for example, this linear model would estimate the market price of a house where the tax assessment was $10,000 and that was 75 years old as about 1.2 million US dollars. Now, I just made up this particular linear model myself as an example, but in general, when we talk about training a linear model, we mean estimating values for the parameters of the model, or coefficients of the model, as we sometimes call them, which are here the constant value 212,000 and the weights 109 and 2,000, in such a way that the resulting predictions for the outcome variable y price for different houses are a good fit to the data from actual past sales. We'll discuss what good fit means shortly. Predicting house price is an example of a regression task using a linear model called, not surprisingly, linear regression. More generally, in a linear regression model, there may be multiple input variables or features, which will denote x0, x1, etc. Each feature, xi, has a corresponding weight, wi. The predicted output, which we denote y hat, is a weighted sum of features, plus a constant term, b hat. I've put a hat over all the quantities here that are estimated during the regression training process. The w hat and b hat values, which we call the train parameters or coefficients, are estimated from training data, and y hat is estimated from the linear function of input feature values and the train parameters. For example, in the simple housing price example we just saw, W0 hat was 109, X0 represented tax paid, W1 hat was negative 20, X1 was house age, and B hat was 212,000. We call these WI values model coefficients or sometimes feature weights, and B hat is called the bias term or the intercept of the model. Here's an example of a linear regression model with just one input variable or feature, x0, on a simple artificial example data set. The blue cloud of points represents a training set of x0, y pairs. In this case, the formula for predicting the output y hat is just w0 hat times x0 plus b hat, which you might recognize as the familiar slope-intercept formula for a straight line, where W0 hat is the slope and B hat is the y-intercept. The gray and red lines represent different possible linear regression models that could attempt to explain the relationship between x0 and y. You can see that some lines are a better fit than others. The better fitting models capture the approximately linear relationship where, as x0 increases, y also increases in a linear fashion. The red line seems especially good. Intuitively, there are not as many blue training points that are very far above or very far below the red linear model prediction. Let's take a look at a very simple form of linear regression model that just has one input variable or feature to use for prediction. In this case, we have the vector x just has a single component. We'll call it x0. That's the input variable, the input feature. And in this case, because there's just one variable, the predicted output is simply the product of the weight W0 with the input variable x0 plus a bias term b. So x0 is the value that's provided. It comes with the data. And so the parameters we have to estimate are W0 and b in order to obtain the parameters for this linear regression model. So this formula may look familiar. It's the formula for a line in terms of its slope. In this case, slope corresponds to the weight W0, and b corresponds to the y-intercept, we call the bias term. So here, the job of the model is to take as input, let's pick a point here along the x-axis. So W0 corresponds to the slope of this line, and b corresponds to the y-intercept of the line. And so by finding these two parameters together define a straight line in this feature space. Now, the important thing to remember is that there's a training phase and a prediction phase. So the training phase, using the training data, is what we'll use to estimate W0 and b. So one widely used method for estimating W and b for a linear regression problem is called least squares linear regression, also known as ordinary least squares. Least squares linear regression finds the line through this cloud of points that minimizes what is called the mean squared error of the model. The mean squared error of the model is essentially the sum of the squared differences between the predicted target value and the actual target value for all the points in the training set. This plot illustrates what that means. The blue points represent points in the training set. The red line here represents the least squares model that was found through this cloud of training points. And these black lines show the difference between the y value that was predicted for a training point based on its x position and the actual y value of the training point. So for example here, this point, let's say, has an x value of negative 1.75. And if we plug it into the formula for this linear model, we get a prediction here at this point on the line, which is somewhere around, let's say, 60. But the actual observed value in the training set for this point was maybe closer to 10. So in this case, for this particular point, the square difference between the predicted target and the actual target would be 60 minus 10 squared. So we can do this calculation for every one of the points in the training set. We can compute this squared difference between the y value we observe in the training set for a point and the y value that we predicted by the linear model given that training point's x value. So each of these can be computed. This squared difference can be computed. And then if we add all these up and divide by the number of training points, take the average, that will be the mean squared error of the model. So the technique of least squares is designed to find the slope, the w value, and the b value, the y-intercept, that minimize this squared error, this mean squared error. One thing to note about this linear regression model is that there are no parameters to control the model complexity. No matter what the value of w and b, the result is always going to be a straight line. This is both a strength and a weakness of the model, as we'll see later. When you have a moment, compare this simple linear model to the more complex regression model learned with k-nearest neighbors regression on the same data set. You can see that linear models make a strong prior assumption about the relationship between the input x and output y. Linear models may seem simplistic, but for data with many features, linear models can be very effective and generalize well to new data beyond the training set. Now the question is, how exactly do we estimate the linear model's w and b parameters so the model is a good fit? Well, the w and b parameters are estimated using the training data, and there are lots of different methods for estimating w and b depending on the criteria you'd like to use for the definition of what a good fit to the training data is and how you want to control model complexity. For linear models, model complexity is based on the nature of the weights w on the input features. Simpler linear models have a weight vector w that's closer to 0, i.e. where more features are either not used at all and have 0 weight, or have less influence on the outcome, a very small weight. Typically, given possible settings for the model parameters, the learning algorithm predicts the target value for each training example, and then computes what is called a loss function for each training example. That's a penalty value for incorrect predictions. A prediction is incorrect when the predicted target value is different than the actual target value in the training set. For example, a squared loss function would return the squared difference between the target value and the actual value as the penalty. The learning algorithm then computes or searches for the set of w-b parameters that minimize the total of this loss function over all training points. The most popular way to estimate w and b parameters is using what's called least squares linear regression, or ordinary least squares. Least squares finds the values of w and b that minimize the total sum of squared differences between the predicted y value and the actual y value in the training set. Or equivalently, it minimizes the mean squared error of the model. Least squares is based on the squared loss function mentioned before. This is illustrated graphically here, where I've zoomed in on the left lower portion of the simple regression data set. The red line represents the least squares solution for w and b through the training data, and the vertical lines represent the difference between the actual y value of a training point, xi, y, and its predicted y value given xi, which lies on the red line where x equals xi. Adding up all the squared values of these differences for all the training points gives the total squared error, and this is what the least squares solution minimizes. Here, there are no parameters to control model complexity. The linear model always uses all of the input variables and always is represented by a straight line. Another name for this quantity is the residual sum of squares. The actual target value is given in yi, and the predicted y hat value for the same training example is given by the right side of the formula using the linear model with the parameters w and b. Let's look at how to implement this in scikit-learn. Linear regression in scikit-learn is implemented by the linear regression class in the sklearn.linearModel module. As we did with other estimators in scikit-learn, like the nearest neighbors classifier and the regression models, we use the train test split function on the original dataset and then create and fit the linear regression object using the training data in XTrain and the corresponding training data target values in YTrain. Here, note that we're doing the creation and fitting of the linear regression object in one line by chaining the fit method with the constructor for the new object. The linear regression fit method acts to estimate the feature weights W, which it calls the coefficients of the model, and it stores this in the coef underscore attribute, and the bias term B, which is stored in the intercept underscore attribute. Note that if a scikit-learn objects attribute ends with an underscore, this means that these attributes were derived from training data and not, say, quantities that were set by the user. If we dump the coef underscore and intercept underscore attributes for this simple example, we see that because there's only one input feature variable, there's only one element in the coef underscore list, the value 45.7. The intercept attribute has a value of about 148.4. And we can see that, indeed, these correspond to the red line shown in the plot, which has a slope of 45.7 and a y-intercept of about 148.4. Here's the same code in the notebook, with additional code to score the quality of the regression model in the same way that we did for k-nearest neighbors regression, using the R-squared metric. And here's the notebook code we used to plot the least squares linear solution for this data set. Now that we've seen both k-nearest neighbors regression and least squares regression, it's interesting now to compare the least squared linear regression results with the k-nearest neighbor results. Here we can see how these two regression methods represent two complementary types of supervised learning. The k-nearest neighbor regressor doesn't make a lot of assumptions about the structure of the data and gives potentially accurate but sometimes unstable predictions that are sensitive to small changes in the training data. So it has a correspondingly higher training set R-squared score compared to least squares linear regression. KNN achieves an R-squared score of 0.72, and least squares achieves an R-squared of 0.679 on the training set. On the other hand, linear models make strong assumptions about the structure of the data. In other words, that the target value can be predicted using a weighted sum of the input variables. And linear models give stable but potentially inaccurate predictions. However, in this case, it turns out that the linear model's strong assumption that there's a linear relationship between the input and output variables happens to be a good fit for this data set. And so it's better at more accurately predicting the y value for new x values that weren't seen during training. And we can see that the linear model gets a slightly better test set score of 0.492 versus 0.471 for k-nearest neighbors. And this indicates its ability to better generalize and capture this global linear trend. Now we'll look at another way to estimate W and B for a linear model, called ridge regression. Ridge regression uses the same least squares criterion, but with one difference. During the training phase, it adds a penalty for feature weights, the WI values, that are too large, as shown in the equation here. You'll see that large weights means mathematically that the sum of their squared values is large. Once ridge regression has estimated the W and B parameters for the linear model, the prediction of y values for new instances is exactly the same as in least squares. You just plug in your input feature values, the xi's, and compute the sum of the weighted feature values plus b with the usual linear formula. So why would something like ridge regression be useful? This addition of a penalty term to a learning algorithm's objective function is called regularization. Regularization is an extremely important concept in machine learning. It's a way to prevent overfitting and thus improve the likely generalization performance of a model by restricting the model's possible parameter settings. Usually the effect of this restriction from regularization is to reduce the complexity of the final estimated model. So how does this work with linear regression? The addition of the sum of squared parameter values that's shown in the box to the least squares objective means that models with larger feature weights W add more to the objective function's overall value. Because our goal is to minimize the overall objective function, the regularization term acts as a penalty on models with lots of large feature weight values. In other words, all things being equal, if ridge regression finds two possible linear models that predict the training data values equally well, it will prefer the linear model that has smaller overall sum of squared feature weights. The practical effect of using ridge regression is to find the feature weights, Wi, that fit the data well in a least squares sense and that set lots of the feature weights to values that are very small. We don't see this effect with a single variable linear regression example, but for regression problems with dozens or hundreds of features, the accuracy improvement from using regularized linear regression like ridge regression can be significant. The amount of regularization to apply is controlled by the alpha parameter. Larger alpha means more regularization and simpler linear models with weights closer to 0. The default setting for alpha is 1.0. Notice that setting alpha to 0 corresponds to the special case of ordinary least squares linear regression that we saw earlier that minimizes the total squared error. In scikit-learn, you use ridge regression by importing the ridge class from sklearn.linearModel and then use that estimator object just as you would for least squares. The one difference is that you can specify the amount of the ridge regression regularization penalty, which is called an L2 penalty, using the alpha parameter. Here, we're applying ridge regression to the crime dataset. Now, you'll notice here that the results are not that impressive. The R-squared score on the test set is pretty comparable to what we got for least squares regression. However, there's something we can do in applying ridge regression that will improve the results dramatically. So now's the time for a brief digression about the need for feature preprocessing and normalization. Let's stop and think for a moment intuitively what ridge regression is doing. It's regularizing the linear regression by imposing that sum of squares penalty on the size of the W coefficients. So the effect of increasing alpha is to shrink the W coefficients towards 0 and towards each other. But if the input variables, the features, have very different scales, then when this shrinkage happens of the coefficients, input variables with different scales will have different contributions to this L2 penalty, because the L2 penalty is the sum of squares of all the coefficients. So transforming the input features so they're all on the same scale means the ridge penalty is in some sense applied more fairly to all features without unduly weighting some more than others, just because of the difference in scales. So more generally, you'll see as we proceed through the course that feature normalization is important to perform for a number of different learning algorithms beyond just regularized regression. This includes k-nearest neighbors, support vector machines, neural networks, and others. The type of feature preprocessing and normalization that's needed can also depend on the data. For now, we're going to apply a widely used form of feature normalization called min-max scaling that will transform all the input variables so they're all in the same scale between 0 and 1. To do this, we compute the minimum and maximum values for each feature on the training data, and then apply the min-max transformation for each feature as shown here. Here's an example of how it works with two features. Suppose we have one feature, height, whose values fall in a fairly narrow range between 1.5 and 2.5 units. But a second feature, width, has a much wider range between 5 and 10 units. After applying min-max scaling, values for both features are transformed so they are on the same scale, with the minimum value getting mapped to 0 and the maximum value being transformed to 1, and everything else getting transformed to a value between those two extremes. To apply min-max scaling in scikit-learn, you import the min-max scalar object from sklearn.preprocessing. To prepare the scalar object for use, you create it and then call the fit method using the training data, xtrain. This will compute the min and max feature values for each feature in this training data set. Then to apply the scaler, you call its transform method and pass in the data you want to rescale. The output will be the scaled version of the input data. In this case, we want to scale the training data and save it in a new variable called xtrain scaled, and the test data, saving that into a new variable called xtest scaled. Then we just use these scaled versions of the feature data instead of the original feature data. Note that it can be more efficient to perform fitting and transforming in a single step on the training set by using the scaler's fit transform method as shown here. There's one last but very important point here about how to apply min-max scaling or any kind of feature normalization in a learning scenario with training and test sets. You may have noticed two things here. First, that we're applying the same scalar object to both the training and the test data. And second, that we're training the scalar object on the training data and not on the test data. These are both critical aspects to feature normalization. If you don't apply the same scaling to training and test sets, you'll end up with more or less random data skew, which will invalidate your results. If you prepare the scalar or other normalization method by showing it the test data instead of the training data, this leads to a phenomenon called data leakage, where the training phase has information that is leaked from the test set, for example, like the distribution of extreme values for each feature in the test data, which the learner should never have access to during training. This in turn can cause the learning method to give unrealistically good estimates on the same test set. We'll look more at the phenomenon of data leakage later in the course. One downside to performing feature normalization is that the resulting model on the transformed features may be harder to interpret. Again, in the end, the type of feature normalization that's best to apply can depend on the data set, learning task, and learning algorithm to be used. We'll continue to touch on this issue throughout the course. Okay, let's return to ridge regression after we've added the code for min-max scaling of the input features. We can see the significant effect of min-max scaling on the performance of ridge regression. After the input features have been properly scaled, ridge regression achieves significantly better model fit with an R-squared value on the test set of about 0.6, much better than without scaling, and much better now than ordinary least squares. In fact, if you apply the same min-max scaling with ordinary least squares regression, you should find that it doesn't change the outcome at all. In general, regularization works especially well when you have relatively small amounts of training data compared to the number of features in your model. Regularization becomes less important as the amount of training data you have increases. We can see the effect of varying the amount of regularization on the scaled training and test data using different settings for alpha in this example. The best R-squared value on the test set is achieved with an alpha setting of around 20. Significantly larger or smaller values of alpha both lead to significantly worse model fit. This is another illustration of the general relationship between model complexity and test set performance that we saw earlier in this lecture, where there's often an intermediate best value of a model complexity parameter that does not lead to either under or overfitting. Another kind of regularized regression that you could use instead of ridge regression is called lasso regression. Like ridge regression, lasso regression adds a regularization penalty term to the ordinary least squares objective that causes the model W coefficients to shrink towards 0. Lasso regression uses a slightly different regularization term called an L1 penalty instead of ridge regression's L2 penalty, as shown here. The L1 penalty looks kind of similar to the L2 penalty in that it computes a sum over the coefficients, but it's a sum over the absolute values of the W coefficients instead of a sum of squares. And the results are noticeably different. With lasso regression, a subset of the coefficients are forced to be precisely 0, which is a kind of automatic feature selection, since with a weight of 0, the feature is essentially ignored completely in the model. This sparse solution, where only a subset of the most important features are left with non-zero weights, also makes the model easier to interpret in cases where there are more than a few input variables. Like ridge regression, the amount of regularization for the lasso regression is controlled by the parameter alpha, which by default is 1.0. Also like ridge regression, the purpose of using lasso regression is to estimate the W and B model coefficients. Once that's done, the prediction model formula is the same as for ordinary least squares. You just use the linear model. In general, lasso regression is most helpful if you think there are only a few variables that have a medium or large effect on the output variable. Otherwise, if there are lots of variables that contribute small or medium effects, ridge regression is typically the better choice. Let's take a look at lasso regression in scikit-learn using the notebook, using our Communities in Crime regression dataset. To use lasso regression, you import the lasso class from sklearn.linearModel, and then just use it as you would use an estimator like ridge regression. With some datasets, you may occasionally get a convergence warning, in which case you can set the max_iter attribute to a larger value, so typically at least 20,000, or possibly more. Increasing the max iter parameter will increase the computation time accordingly. In this example, we're applying lasso to a min-max scaled version of the crime dataset as we did for ridge regression. You can see that for alpha set to 2.0, only 20 features with non-zero weights remain because with lasso regularization, most of the features are set to have weights of exactly 0. I've listed the features with non-zero weights in order of their descending magnitude from the output. Although we need to be careful in interpreting any results for data on a complex problem like crime, the lasso regression results do help us see some of the strongest relationships between the input variables and outcomes for this particular dataset. For example, looking at the top 5 features with non-zero weight that are found by lasso regression, we can see that location factors like percentage of people in dense housing, which indicates urban areas, and socioeconomic variables like the fraction of vacant houses in an area are positively correlated with crime. And other variables like the percentage of families with 2 parents is negatively correlated. Finally, we can see the effect of tuning the regularization parameter alpha for lasso regression. Like we saw with ridge regression, there's an optimal range for alpha that gives the best test set performance that neither under or overfits. Of course, this best alpha value will be different for different data sets and depends on various other factors such as the feature preprocessing methods being used. Let's suppose for a moment that we had a set of 2-dimensional data points with features x0 and x1. Then we could transform each data point by adding additional features that were the 3 unique multiplicative combinations of x0 and x1. So x0 squared, x0, x1, and x1 squared. So we've transformed our original 2-dimensional points into a set of 5-dimensional points that rely only on the information in the 2-dimensional points. Now we can write a new regression problem that tries to predict the same output variable, y hat, but using these 5 features instead of 2. The critical insight here is that this is still a linear regression problem. The features are just numbers within a weighted sum. So we can use the same least squares techniques to estimate the 5 model coefficients for these 5 features that we used in the simpler 2-dimensional case. Now, why would we want to do this kind of transformation? Well, this is called polynomial feature transformation that we can use to transform a problem into a higher dimensional regression space. And in effect, adding these extra polynomial features allows us a much richer set of complex functions that we can use to fit to the data. So you can think of this intuitively as allowing polynomials to be fit to the training data instead of simply a straight line, but using the same least squares criterion that minimizes mean squared error. We'll see later that this approach of adding new features like polynomial features is also very effective with classification, and we'll look at this kind of transformation again in kernelized support vector machines. When we add these new polynomial features, we're essentially adding to the model's ability to capture interactions between the different variables by adding them as features to the linear model. For example, it may be that housing prices vary as a quadratic function of both the lot size that a house sits on and the amount of taxes paid on the property, as a theoretical example. A simple linear model could not capture this nonlinear relationship. But by adding nonlinear features like polynomials to the linear regression model, we can capture this nonlinearity. More generally, we can use other types of nonlinear feature transformations beyond just polynomials. This is beyond the scope of this course, but technically these are called nonlinear basis functions for regression and are widely used. Of course, one side effect of adding lots of new features, especially when we're taking every possible combination of k variables, is that these more complex models have the potential for overfitting. So in practice, polynomial regression is often done with a regularized learning method like ridge regression. Here's an example of polynomial regression using scikit-learn. There's already a handy class called polynomial features in the sklearn.preprocessing module that will generate these polynomial features for us. This example shows 3 regressions on a more complex regression dataset that happens to have some quadratic interactions between variables. The first regression here just uses least squares regression without the polynomial feature transformation. The second regression creates the polynomial features object with degree set to 2, and then calls the fit transform method of the polynomial features object on the original xf1 features to produce the new polynomial transform features xf1 poly. The code then calls ordinary least squares linear regression. You can see indications of overfitting on this expanded feature representation as the model's R² score on the training set is close to 1, but much lower on the test set. So the third regression shows the effect of adding regularization via ridge regression on this expanded feature set. Now the training and test R² scores are basically the same, with the test set score of the regularized polynomial regression performing the best of all 3 regression methods. I'd like to take a minute to show you a very useful and interesting plot that shows how the choice of the regularization parameter alpha affects the estimated coefficients of the regression model. I'll call this a coefficient curve plot. So recall that if we want to fit a regularized regression model, such as ridge or lasso regression, to a set of points, we also specify a particular value of alpha to use that controls how much weight is given to the regularization penalty in the optimization objective. So in this part of the slide, I've written down the optimization objective, and you can see that we have the regularization parameter alpha that controls how much weight the regularization part of the objective gets, this sum of wj squareds, compared to the normal least squares part of the objective. So we specify alpha, we fit the model, and like all regression scenarios, the result of fitting the model will be a set of estimated coefficients. So in this example, we're imagining that we have 6 model weights that go, let's say, with 6 different features in the input. And we're going to be analyzing a linear model that estimates these 6 coefficients, W1 through W6, that we're fitting with ridge regression in this case. I'm going to ignore the coefficient B here in the plot since that doesn't contribute to the regularization penalty. Okay, so here is the coefficient curve plot for this example of ridge regression. On the x-axis, over here, we have the value of alpha. Now, note that I'm plotting this on a logarithmic scale because we're varying alpha quite widely between a relatively small value and a relatively large value. So just take note of that logarithmic scale. On the y-axis of this plot, we have the value of an estimated coefficient. And because we have 6 coefficients, I've plotted 6 curves on this plot. So there's one curve for each estimated coefficient, W1, W2, and so forth. Now this chart shows what happens to an estimated coefficient as we fit the model using different choices for alpha. In fact, this coefficient curve plot shows every possible choice for alpha between 10 to the minus 1 down here all the way up to 100. And we smoothly vary out. We pretend that we can compute an infinite number of possible models using any choice of alpha we like, and this creates a curve as a function of alpha. For example, the plot shows that for ridge regression, if we pick alpha equal to 10 to the minus 1, then we get a model whose estimate for W1 will be just a little bit less than 50. If we pick alpha equal to 10, we look here at the values. This plot shows that the resulting model will have an estimated coefficient for W1 that's around 28. And it shows what the values of the other estimated coefficients will be as well. So you can see that as we increase our choice value for alpha, the value of the estimated coefficient W1 gets smaller and smaller. It shrinks, and that's basically what ridge regression does. It penalizes coefficient values that are larger using this squared penalty term. And thus it forces the model to shrink the estimated coefficient towards 0. The more weight that you give to that regularization term, the higher the value of alpha, the more you're emphasizing that the estimated coefficients must be small. And if we do this for all 6 coefficients, this plot shows the shrinkage effect that ridge regression has as we increase alpha. Here's the corresponding coefficient curve plot for the same linear model, but this time we fit it using lasso regression, which uses an L1 regularization penalty term. So you can see the L1 penalty term here, and just as in ridge regression, the parameter alpha controls how much weight the objective places on the regularization part versus the ordinary least squares part. Notice that when alpha is very small, so like 10 to the minus 1, the values of the resulting estimated coefficients, W1, W2, and so forth, on the left here are effectively the same as we saw in ridge regression, right? Because the regularization penalty alpha is very small in both cases, so we'll get something close to the ordinary least squares solution. So lasso and ridge regression will produce models with estimated coefficients that are very similar when alpha is very small. But as we increase alpha, we can see this shrinkage effect on the estimated coefficients is very different for lasso regression compared to ridge regression. We can see how lasso regression finds sparse sets of coefficients for higher values of alpha. For example, this time if we choose alpha to be 10, so suppose we fit a model using alpha equals 10, the resulting estimated coefficients will be the values along this line. And you can see that the resulting coefficients for W2 here, W3, and W5, they've already shrunk to 0. So by the time we get to alpha equals 10, the models that are being produced at alpha equals 10 have W2, W3, and W5 equal to 0. The only coefficients in the model that will have non-zero values will be the remaining coefficients, W1, W4, and W6. Okay, so at alpha equals 10, you can see that those are just ever so slightly non-zero. If we choose alpha equal 30, which is going to be somewhere here, if we fit the model using lasso regression with alpha set to 30, the only non-zero estimated coefficient at that point will be W1. So you can see that's why lasso regression gives these very sparse solutions. You can see that that's a really nice illustration of the lasso shrinkage effect as a function of alpha. So these coefficient curves are a really nice way to show what's called the entire solution path for a model as a function of the regularization hyperparameter alpha. And that lets us compare how different regularization penalties shrink the estimated model coefficients in different ways. We're now going to look at a second supervised learning method that, in spite of being called a regression method, is actually used for classification, and it's called logistic regression. Logistic regression can be seen as a kind of generalized linear model. And like ordinary least squares and other regression methods, logistic regression takes a set of input variables, the features, and estimates a target value. However, unlike ordinary linear regression, in its most basic form, logistic regression's target value is a binary variable instead of a continuous value. There are flavors of logistic regression that can also be used in cases where the target value to be predicted is a multi-class categorical variable, not just binary. But for now, we'll focus on the simple binary case of logistic regression. Let's start by looking at linear regression, which we saw earlier. Linear regression predicts a real valued output y based on a weighted sum of input variables or features, xi, plus a constant b term. This diagram shows that formula in graphical form. The square boxes on the left represent the input features, xi, and the values above the arrows represent the weights that each xi is multiplied by. The output variable y in the box on the right is the sum of all the weighted inputs that are connected into it. Note that we're adding b as a constant term by treating it as the product of a special constant feature with value 1 multiplied by a weight of value b. This formula is summarized in equation form below the diagram. The job of linear regression is to estimate values for the model coefficients wi hat and b hat that give a model that best fit the training data with minimal squared error. Logistic regression is similar to linear regression, but with one critical addition. Here we show the same type of diagram that we showed for linear regression, with the input variables xi in the left boxes and the model coefficients wi and b above the arrows. The logistic regression model still computes a weighted sum of the input features xi and the intercept term b, but it runs this result through a special nonlinear function f, the logistic function, represented by this new box in the middle of the diagram to produce the output y. The logistic function itself is shown in more detail on the plot on the right. It's an S-shaped function that gets closer and closer to 1 as the input value increases above 0, and closer to 0 as the input value decreases far below 0. The effect of applying the logistic function is to compress the output of the linear function so that it's limited to a range between 0 and 1. Below the diagram, you can see the formula for the predicted output y hat, which first computes the same linear combination of the inputs xi, model coefficient weights wi hat, and intercept b hat, but runs it through the additional step of applying the logistic function to produce y hat. If we pick different values for b hat and the w hat coefficients, we'll get different variants of this S-shaped logistic function, which again is always between 0 and 1. Because the job of basic logistic regression is to predict a binary output value, you can see how this might be used for binary classification. We could identify data instances with a target value of 0 as belonging to the negative class, and data instances with a target value of 1 as belonging to the positive class. Then, the value of y hat, that's the output from the logistic regression formula, can be interpreted as the probability that the input data instance belongs to the positive class given its input features. Let's look at a specific example of logistic regression with one input variable. Suppose we want to predict whether or not a student will pass a final exam based on a single input variable that's the number of hours they spend studying for the exam. Students who end up failing the exam are assigned to the negative class, which corresponds to a target value of 0, and students who pass the exam are assigned to the positive class and associated with a target value of 1. This plot shows an example training set. The x-axis corresponds to the number of hours studied, and the y-axis corresponds to the probability of passing the exam. The red points to the left with a target value of 0 represent points in the training set which are examples of students who failed the exam along with the number of hours they spent studying. Likewise, the blue points with target value 1 on the right represent points in the training set corresponding to students who passed the exam, with their x values representing the number of hours those students spent studying. Using logistic regression, we can estimate model coefficients for w hat and b hat that produce a logistic curve that best fits these training points. In this example, that logistic curve might look something like this. Once the model coefficients have been estimated, we now have a formula that can use the resulting logistic function to estimate the probability that any given student will pass the exam, given the number of hours they've studied. Students whose estimated probability of passing the exam is greater than or equal to 50% are predicted to be in the positive class. Otherwise, they're predicted to be in the negative class. So in this example, we can see that students who study for more than 3 hours will be predicted to be in the positive class. Let's look at an example that uses 2 input features now instead of 1. Here, the plots show a training set with 2 classes. Each data point has 2 features. Feature 1 corresponds to the x-axis, and feature 2 corresponds to the y-axis. The data points in the red class on the left form a cluster with low feature 1 value and high feature 2 value. And the points in the blue class have intermediate feature 1 value and low feature 2 value. We can apply logistic regression to learn a binary classifier using this training set, using the same idea we saw in the previous exam example. To do this, we'll add a third dimension, shown here as the vertical y-axis, corresponding to the probability of belonging to the positive class. We'll say that the red points are associated with the negative class and have a target value of 0, and the blue points are associated with the positive class and have a target value of 1. Then, just as we did in the exam studying example, we can estimate the w hat and b hat parameters of a logistic function that best fits this training data. The only difference is that the logistic function is now a function of 2 input features and not just 1. So it forms something like a 3-dimensional S-shaped sheet in this space. Once this logistic function has been estimated from the training data, we can use it to predict the class membership for any point given its feature 1 and feature 2 values, same way we did for the exam example. Any data instances whose logistic probability estimate y hat is greater than or equal to 0.5 are predicted to be in the positive blue class, otherwise in the other red class. Now if we imagine that there's a plane representing y equals 0.5, as shown here, that intersects this logistic function, it turns out that all the points that have a value of y equals 0.5, when you intersect that with a logistic function, the points all lie along a straight line. In other words, using logistic regression gives a linear decision boundary between the classes, as shown here. If you imagine looking straight down on the 3D logistic function on the left, you get the view that looks something like something on the right here. The points with y greater than or equal to 0.5 on the logistic function lie in a region to the right of the straight line, which is the dashed line on the right here. And the points with y less than 0.5 on the logistic function would form a region to the left of that dashed line. Let's look at an example with real data in scikit-learn. To perform logistic regression in scikit-learn, you import the logistic regression class from the sklearn.linearModel module, and then create the object and call the fit method using the training data just as you did for other classifiers like k-nearest neighbors. Here the code also sets a parameter c to 100, which we'll explain in a minute. The dataset we're using here is a modified form of our fruits dataset, using only height and width as the features in the feature space, and with the target class values modified into a binary classification problem, predicting whether an object is an apple, the positive class, or something other than an apple, the negative class. Here's a graphical display of the results. The x-axis corresponds to the height feature, and the y-axis corresponds to the width feature. The black points represent the positive apple class training points, and the yellow points are instances of all the other fruits in the training set. The gray decision region represents that area of the height and width feature space where a fruit would have an estimated probability greater than 0.5 of being an apple, and thus classified as an apple, according to the logistic regression function. The yellow decision region corresponds to the region of feature space for objects that have an estimated probability of less than 0.5 of being an apple. You can see the linear decision boundary where the gray region meets the yellow region that results from applying logistic regression. In fact, logistic regression results are often quite similar to those you might obtain from a linear support vector machine, another type of linear model we explore for classification. Like ridge and lasso regression, a regularization penalty on the model coefficients can also be applied with logistic regression and is controlled with the parameter c. In fact, the same L2 regularization penalty used for ridge regression is turned on by default for logistic regression with a default value c equals 1. Note that for both support vector machines and logistic regression, higher values of c correspond to less regularization. With large values of c, logistic regression tries to fit the training data as well as possible, while with small values of c, the model tries harder to find model coefficients that are closer to 0, even if that model fits the training data a little bit worse. You can see the effect of changing the regularization parameter c for logistic regression in this visual. Using the same apple classifier, we now vary c to take on values from 0.1 on the left to 1.0 in the middle and 100.0 on the right. Although the real power of regularization doesn't become evident until we have data that has higher dimensional feature spaces, you can get an idea of the trade-off that's happening between relying on a simpler model, one that puts more emphasis on a single feature in this case, out of the two features, but has lower training set accuracy. And that's an example as shown on the left with c equal 0.1. Or better training data fit on the right with c equal 100. You can find the code that created this example in the accompanying notebook. Finally, we show how logistic regression, again with L2 regularization turned on by default, can be applied to a real data set with many more features, the breast cancer data set. Here, logistic regression achieves both training and test set accuracy of 96%. Let's look at how linear models are also used for classification, starting with binary classification. This approach to prediction uses the same linear functional form as we saw for regression, but instead of predicting a continuous target value, we take the output of the linear function and apply the sign function to produce a binary output with two possible values, corresponding to the two possible class labels. If the target value is greater than 0, the function returns +1, and if it's less than 0, the function returns -1. Here's a specific example. So let's take a look at a simple linear classification problem, a binary problem that has two different classes and where each data instance is represented by two informative features. So we're going to call these features x1 on the x-axis and x2 on the y-axis. Now, how do we get from taking a data instance that's just described by a particular combination of x1, x2 to a class prediction? Well, in a linear classifier, what we do is we take the feature values assigned to a particular data point. So in this case, it might be 2.10, So that represents the x1 and x2 feature values for this particular instance, let's say. And so that corresponds to the input here. And then we take those two x1, x2 values and put them through a linear function f here. And the output of this f needs to be a class value. So either we want it to return +1 if it's in one class and -1 if it's in the other class. So the linear classifier does that by computing a linear function of x1, x2. That's represented by this part of the equation here. So this w is a vector of weights. This x represents the vector of feature values, and then b is a bias term that gets added in. So this is a dot product. This circle here is a dot product, which means that, let's say in the simple case where we had weight vector 1 and 2, and a feature vector of x1, x2, the dot product of those is simply the linear combination of w1, x1 plus w2, x2. And then, so we take the x values, and we have certain weights that are learned for the classifier. So we compute w1, x1 plus w2, x2, and then we feed that, and then plus a bias term if there is one. And we feed the output of that through this sine function that converts the value in here. If it's above 0, it'll convert it to +1, and if it's below 0, it'll convert it to -1. And that's what the equation represents here. So that is the very simple rule that we use to convert a data instance with its input features to an output prediction. Okay, let's take a look using a specific linear function to see how this works in practice. So what I've done here is drawn a straight line through this space that it's defined by the equation x1 minus x2 equals 0. In other words, every point on this line satisfies this equation. So you can see, for example, that x1 equals -1 and x2 equals -1, and if you subtract them, you get 0. Essentially, it's just the line that represents all the points where x1 and x2 are equal. So this corresponds to, so we can sort of rewrite this x1 minus x2 equals 0 into a form that uses a dot product of weights with the input vector x. So in order to get x1 minus x2 equals 0, that's equivalent to writing a linear function where you have a weight vector of 1 and -1 and a bias term of 0. So for example, so if we have weights w1, w2, and dot product of x1, x2, recall that this is just the same as computing w1, x1 plus w2, x2. And so in this case, if w is 1 and -1, that's equivalent to x1 minus x2. So all I've done here then is just convert the description of this line into a form that can be used as a decision rule for a classifier. So it might help to look at a specific point. So suppose that we wanted to classify the point here that had coordinates -0.75 and -2.25. So this point right here. So all we would do to have the classifier make a prediction with this decision boundary would be to plug in those coordinates into this part of the function, apply the weights and the bias term that describe the decision boundary. So here we're computing, so this expression here corresponds to this part of the equation. And so if we compute weight 1 times x1 plus weight 2 times x2 plus 0, we get a value of 0.15 that's inside the sine function, and then the sine function will output 1 if this value is greater than 0, which it is, or minus 1 if the value is less than 0. So in this case, because it's greater than 0, the output from the decision function would be plus 1. So this has classified this point as being of class 1. If we look at a different point, let's take a look at the point negative 1.75 and negative 0.25. So again, we're just going to, so this is corresponding to the value of x1 and x2. And again, if we just take these values and plug them into this part of the equation, apply the weights and the bias term that describe the decision boundaries that we did before, we do this computation, we find out that, in fact, the classifier predicts a class of -1 here. So you see that by applying a simple linear formula, we've been able to produce a class value for any point in this two-dimensional feature space. So one way to define a good classifier is to reward classifiers for the amount of separation they can provide between the two classes. And to do this, we need to define the concept of classifier margin. So informally, for our given classifier, the margin is the width that the decision boundary can be increased before hitting a data point. So what we do is we take the decision boundary and we grow a region around it that sort of in perpendicular to the line this direction and that direction, and we grow this width until we hit a data point. So in this case, we were only able to grow the margin a small amount here before hitting this data point. So this width here between the decision boundary and the nearest data point represents the margin of this particular classifier. Now you can imagine that for every classifier that we tried, we can do the same kind of calculation or simulation to find the margin. And so among all possible classifiers that separate these two classes then, we can define the best classifier as the classifier that has the maximum amount of margin, which corresponds to the one shown here. So you recall that the original classifier on the previous slide had a very small margin. This one manages to achieve a much larger margin. So again, the margin is the distance, the width that we can go from the decision boundary perpendicular to the nearest data point. And so you can see that by defining this concept of margin, it sort of quantifies the degree to which the classifier can split the classes into two regions that have some amount of separation between them. We can actually do a search for the classifier that has the maximum margin. And this maximum margin classifier is called a linear support vector machine, also known as an LSVM or a support vector machine with linear kernel. Now we'll explain more about what the concept of a kernel is and how you can define nonlinear kernels as well as kernels and why you'd want to do that. We'll cover those shortly in a continuation of our support vector machine lecture later in this particular week. Here's an example in the notebook on how to use the default linear support vector classifier in scikit-learn, which is defined in the sklearn SVM library. The linear SVC class implements a linear support vector classifier and is trained in the same way as other classifiers, namely by using the fit method on the training data. Now, in the simple classification problem I just showed you, the two classes were perfectly separable with a linear classifier. In practice, though, we typically have noise or just more complexity in the data set that makes a perfect linear separation impossible. But where most points can be separated without errors by a linear classifier. And our simple binary classification data set here is an illustration of that. So how tolerant the support vector machine is of misclassifying training points as compared to its objective of minimizing the margin between classes, is controlled by a regularization parameter called C, which by default is set to 1.0, as we have here. Larger values of C represent less regularization and will cause the model to fit the training set with as few errors as possible, even if it means using a smaller margin decision boundary. Very small values of C, on the other hand, use more regularization that encourages the classifier to find a large margin decision boundary, even if that decision boundary leads to more points being misclassified. Here's an example in the notebook showing the effect of varying C on this basic classification problem. On the right, when C is large, the decision boundary is adjusted so that more of the black training points are correctly classified, while on the left, for small values of C, the classifier is more tolerant of these errors in favor of capturing the majority of data points correctly with a larger margin. Finally, here's an example of applying the linear support vector machine to a real-world data set, the breast cancer classification problem. And here we can see it achieves reasonable accuracy without much parameter tuning. On the positive side, linear models, in the case of linear and logistic regression, are simple and easy to train. And for all types of linear models, prediction's very fast because of the linear nature of the prediction function. Linear models, including linear support vector machines, also perform effectively on high-dimensional data set, especially in cases where the data instances are sparse. Linear models scale well to very large data sets as well. In the case of linear support vector machines, they only use a subset of training points in the decision function. These training points are called support vectors, so the algorithm can be implemented in a memory-efficient way. In the examples we've used so far for classification, we've primarily focused on binary classification, where the target value to be predicted was a binary value. It was either a positive or a negative class. In a lot of real-world data sets, the target value to be predicted is actually a category. So for example, in our fruit data set, there were 4 different categories of fruit to be predicted, not just 2. So how do we deal with this multi-class classification situation with scikit-learn? Well, fortunately, scikit-learn makes it very easy to learn multi-class classification models. Essentially, it does this by converting a multi-class classification problem into a series of binary problems. What do I mean by that? Well, essentially when you pass in a data set that has a categorical variable for the target value, scikit-learn detects this automatically. And then for each class to be predicted, scikit-learn creates one binary classifier that predicts that class against all the other classes. So for example, in the fruit data set, there are 4 categories of fruit, so scikit-learn learns 4 different binary classifiers. To predict a new data instance, what it then does is takes that data instance to be predicted, whose label is to be predicted, and runs it against each of the binary classifiers in turn. And the classifier that has the highest score is the one that whose class it uses as the prediction value. So let's look at a specific example of multi-class classification with this fruit data set. Here we simply pass in the normal data set that has the value from 1 to 4 as the category of fruit to be predicted. And we fit it exactly the same way that we would fit the model as if it were a binary problem. And in general, if we're just fitting and then predicting, all of this would be completely transparent. Scikit-learn would simply do the right thing, and it would learn multiple classes, and it would predict multiple classes, and we wouldn't really have to do much else. However, we can get access to what's happening under the hood, as it were, if we look at the coefficients and the intercepts of the linear models that result from fitting to the training data. And this is what this example shows. So what we're doing here is fitting a linear support vector machine to the fruit training data. And if we look at the coefficient values, we'll see that instead of just one pair of coefficients for a single linear model classifier, we actually get 4 values. And these values correspond to the 4 classes of fruit in the training set. And so what scikit-learn has done here is it's created 4 binary classifiers, 1 for each class. And so you can see there are 4 pairs of coefficients here, and there are also 4 intercept values. So in this case, the first pair of coefficients corresponds to a classifier that classifies apples versus the rest of the fruit. And so these pair of coefficients and this intercept define a straight line. In this case, it's this. So the apples in this visual are the red points. And so the coefficients of the apple model define a decision boundary, a linear decision boundary, that's marked by this red line here. And if you plot it out, you'll see that indeed it has an intercept of -3, and it's, you can actually compute for any data instance using this linear formula what it'll predict, either apple or not an apple. So if we take a specific example, something that has a height of 2 and a width of 6, so some query point here, for example. This is a linear classifier, so we can take the coefficients, this first pair of coefficients here, and this first intercept value here, and these form a linear classifier for apples versus not apples. So we can take the height feature, multiply it by the first coefficient, take the width feature, multiply it by the second coefficient, and then add in the third intercept feature, this third bias term. And so to predict whether this object that has height of 2 and width of 6 is an apple, we simply compute this linear formula. It turns out that the value is positive 0.59. And so because that value is greater than or equal to 0, that indicates that the model is predicting that the object is indeed an apple. And that makes sense because it's on this side of the apple versus not apple binary classifier decision boundary. Similarly, we can take another object, say one who has a height of 2 and a width of 2, so in this part of the space over here. And we can plug in those 2 feature values into the same apple classifier. And when we do that, it turns out that the prediction value of the linear model in that case is -2.3, and that's less than 0, which is on this side of the decision boundary. And so the linear model for apple versus not apple here is predicting that this object is not an apple. And so, again, when scikit-learn has to predict the class of a new object with potentially multiple classes, it will go through each of these binary classifiers in turn, and it will predict the class whose classifier has the highest score for that instance. We saw earlier how linear support vector machines served as effective classifiers for some data sets by finding a decision boundary with maximum margin between the classes. Linear support vector machines worked well for simpler kinds of classification problems where the classes were linearly separable or close to linearly separable, like this example on the left. But with real data, many classification problems aren't this easy, with the different classes located in feature space in a way that a line or hyperplane can't act as an effective classifier. Here's an example on the right. This data set is difficult or impossible for a linear model, a line or a hyperplane, to classify well. So to help address the situation, we're now going to turn to our next type of supervised learning model, a very powerful extension of linear support vector machines called kernelized support vector machines. Basically, kernelized support vector machines, which I'll just call SVMs, can provide more complex models that go beyond linear decision boundaries. As with other supervised machine learning methods, SVMs can be used for both classification and regression. But due to time constraints, we'll focus only on classification in this lecture. We also won't go into the mathematical details of how SVMs operate, but we will give a high-level overview that hopefully captures the most important elements of this method. In essence, one way to think about what kernelized SVMs do is that they take the original input data space and transform it to a new higher dimensional feature space, where it becomes much easier to classify the transformed data using a linear classifier. Here's a simple one-dimensional example of what I mean. Here's a binary classification problem in one dimension with a set of points that lie along the x-axis, colored black for one class and white for the second class. Each data point here has just one feature, its position on the x-axis. If we gave this problem to a linear support vector machine, it would have no problem finding the decision boundary that gives the maximal margin between points of different classes. Here I've engineered the data points so that the maximum margin decision boundary happens to be at x equals 0. Now suppose we gave the linear support vector machine a harder problem, where the classes are no longer linearly separable. A simple linear decision boundary just doesn't have enough expressive power to classify all these points correctly. So what can we do about this? One very powerful idea is to transform the input data from a one-dimensional space to a two-dimensional space. We can do this, for example, by mapping each one-dimensional input data instance, xi, to a corresponding two-dimensional ordered pair, xi squared, whose new second feature is the squared value of the first feature. We're not adding any new information in the sense that all we need to obtain this new two-dimensional version is already present in the original one-dimensional data point. This might remind you of a similar technique that we saw when adding polynomial features to a linear regression problem earlier in the course. We can now learn a linear support vector machine in this new two-dimensional feature space, whose maximum margin decision boundary might look like this here, to correctly classify the points. Any future one-dimensional points for which we'd like to predict the class, we can just create the two-dimensional transformed version and predict the class of the two-dimensional point using this two-dimensional linear SVM. If we took the inverse of the transformation we just applied to bring the data points back to our original input space, we can see that the linear decision boundary in the two-dimensional space corresponds to the 2 points where a parabola crosses the x-axis. Now, just so this very important idea is clear, let's move from a one-dimensional problem to a two-dimensional classification problem and see the same powerful idea in action here. Here we have two classes represented by the black and the white points, each of which has two features, x0 and x1. The points of both classes are scattered around the origin, 0, 0, in a two-dimensional plane. The white points form a cluster right around 0, 0 that's completely surrounded by the black points. Again, this looks to be impossible for a linear classifier, which in two-dimensional space is a straight line, to separate the white points from the black points with any degree of accuracy. But just as we did in the one-dimensional case, we can map each two-dimensional point, x0, x1, to a new three-dimensional point by adding a third feature, mathematically 1 minus x0 squared plus x1 squared. And this transformation acts to shape the points into a paraboloid around 0, 0. Now the white points, since they're close to 0, 0, get mapped to points with higher vertical z values, that new third feature, that are close to 1. While the black points, which are farther from 0, 0, get mapped to points with z values that are either close to 0 or even negative. With this transformation, it makes it possible to find a hyperplane, say z equals 0.9, that now easily separates the white data points that are near z equals 1 from most or all of the black data points. Finally, the decision boundary consists of the set of points in 3D space where the paraboloid intersects the maximum margin hyperplane decision boundary. This corresponds to an ellipse-like decision boundary in 2D space that separates the white points from the black points in the original input space. This idea of transforming the input data points to a new feature space where a linear classifier can be easily applied is a very general and powerful one. There are lots of different possible transformations we could apply to data. And the different kernels available for the kernelized SVM correspond to different transformations. Here we're going to focus mainly on what's called the radial basis function kernel, which we'll abbreviate as RBF. And also look briefly at something called a polynomial kernel that's also included with scikit-learn's SVM module. The kernel function in an SVM tells us, given 2 points in the original input space, what is their similarity in the new feature space. For the radial basis function kernel, the similarity between 2 points in the transformed feature space is an exponentially decaying function of the distance between the vectors in the original input space, as shown by the formula here. So what does the radial basis function feature transformation look like? Well, this diagram should give an intuitive idea. Here's another graphical illustration of a binary classification problem. And again, this diagram is for illustration purposes only, and it's just an approximation. But essentially, you can think of it in a similar way to the 2D to 3D example we saw earlier. So on the left, there's a set of samples in the input space. The circles represent the training points of one class, and the squares represent training points of a second class. On the right, the same samples are shown in the transformed feature space. Using the radial basis function kernel, in effect, transforms all the points inside a certain distance of the circle class to one area of the transformed feature space, and all the points in the square class outside a certain radius get moved to a different area of the feature space. The dark circles and squares represent the points that might lie along the maximum margin for a support vector machine in the transformed feature space. And also it shows the corresponding points in the original input space. So just as we saw with the simple 1D and 2D examples earlier, the kernelized support vector machine tries to find the decision boundary with maximum margin between classes using a linear classifier in the transformed feature space, not the original input space. The linear decision boundary, learned in feature space by a linear SVM, corresponds to a nonlinear decision boundary in the original input space. So in this example, an ellipse-like closed region in the input space. Now, one of the mathematically remarkable things about kernelized support vector machines, something referred to as the kernel trick, is that internally the algorithm doesn't have to perform this actual transformation on the data points to the new high-dimensional feature space. Instead, the kernelized SVM can compute these more complex decision boundaries just in terms of similarity calculations between pairs of points in the high-dimensional space, where the transformed feature representation is implicit. This similarity function, which mathematically is a kind of dot product, is the kernel in kernelized SVM. And for certain kinds of high-dimensional spaces, the similarity calculation between points, the kernel function, can have a simple form, like we see with the radial basis function calculation. This makes it practical to apply support vector machines when the underlying transformed feature space is complex or even infinite dimensional. Even better, we can easily plug in a variety of different kernels, choosing one to suit the properties of our data. Again, different choices of kernel correspond to different types of transformations to that higher dimensional feature space. Here's the result of using a support vector machine with RBF kernel on that more complex binary classification problem we saw earlier. You can see that unlike a linear classifier, the SVM with RBF kernel finds a more complex and very effective set of decision boundaries that are very good at separating one class from the other. Note that the SVM classifier is still using a maximum margin principle to find these decision boundaries, but because of the nonlinear transformation of the data, these boundaries may no longer always be equally distant from the margin edge points in the original input space. Now let's look at an example of how we did this using scikit-learn in Python. To use SVMs, we simply import the svc class from sklearn.svm and use it just as we would any other classifier, for example, by calling the fit method with the training data to train the model. There is an svc parameter called kernel that allows us to set the kernel function used by the SVM. By default, the SVM will use the radial basis function, but a number of other choices are supported. Here in the second example and plot, we show the use of the polynomial kernel instead of the RBF kernel. The polynomial kernel, using the kernel poly setting, essentially represents a feature transformation similar to the earlier quadratic example. In the lecture, this feature space represented in terms of features that are polynomial combinations of the original input features, much as we saw also for linear regression. The polynomial kernel takes an additional parameter, degree, that controls the model complexity and the computational cost of this transformation. You may have noticed that the RBF kernel has a parameter, gamma. Gamma controls how far the influence of a single training example reaches, which in turn affects how tightly the decision boundaries end up surrounding points in the input space. Small gamma means a larger similarity radius, so that points farther apart are considered similar, which results in more points being grouped together and smoother decision boundaries. On the other hand, for larger values of gamma, the kernel value decays more quickly, and points have to be very close to be considered similar. This results in more complex, tightly constrained decision boundaries. You can see the effect of increasing gamma, that is, sort of sharpening the kernel, in this example from the notebook. Small values of gamma give broader, smoother decision regions, while larger values of gamma give smaller, more complex decision regions. You can set the gamma parameter when creating the SVC object to control the kernel width in this way, as shown in this code. You may recall from linear SVMs that SVMs also have a regularization parameter, C, that controls the trade-off between satisfying the maximum margin criterion to find a simple decision boundary and avoiding misclassification errors on the training set. The C parameter is also an important one for kernelized SVMs, and it interacts with the gamma parameter. This example from the notebook shows the effect of varying C and gamma together. If gamma is large, then C will have little to no effect, while if gamma is small, the model is much more constrained and the effect of C will be similar to how it would affect a linear classifier. Typically, gamma and C are tuned together, with the optimal combination typically in an intermediate range of values, for example, gamma between 0.0001 and 10, and C between 0.1 and 100, though the specific optimal values will depend on your application. Kernelized SVMs are pretty sensitive to settings of gamma. The most important thing to remember when applying SVMs is that it's important to normalize the input data so that all the features have comparable units that are on the same scale. We saw this earlier with some other learning methods like regularized regression. Let's apply a support vector machine with RBF kernel to a real-world data set to see why this normalization is important. Here, we'll apply a support vector machine with RBF kernel to the breast cancer data set. Note that we're not touching the input data in any way. We're simply passing in the raw values. We can see the results with training set accuracy of 1.00 and the test set accuracy of 0.63 that show that the support vector machine is overfitting. It's doing well on the training data, but very poorly on the test data. Now let's add a min-max scalar transformation of the training data, remembering to also apply the same scalar to the test data. After this scalar has been applied, all the input features now lie in the same range, 0 to 1. And looking at these new results, the test set accuracy is much, much higher, at 96%. This illustrates what a huge difference normalizing the features of the training data can have on SVM performance. Let's review the strengths and weaknesses of support vector machines. On the positive side, support vector machines perform well on a range of data sets and have been successfully applied on data that ranges from text to images and many more types. The support vector machine is also potentially very versatile due to its ability to specify different kernel functions, including possible custom kernel functions depending on the data. Support vector machines also typically work well for both low and high dimensional data, including data with hundreds, thousands, or even millions of sparse dimensions. This makes it well suited to text classification, for example. On the negative side, as the training set size increases, the runtime speed and memory usage in the SVM training phase also increases. So for large data sets with hundreds of thousands or millions of instances, an SVM may become less practical. As we saw when applying a support vector machine to a real-world data set, using an SVM requires careful normalization of the input data as well as parameter tuning. The inputs should be normalized so that all features have comparable units and are on similar scales if they aren't already. Support vector machines also don't provide direct probability estimates for predictions, which are needed for some applications. Now, there are ways to estimate these probabilities using techniques such as Platt scaling, which transforms the output of the classifier to a probability distribution over classes by fitting a logistic regression model to the classifier scores. Finally, it can be difficult to interpret the internal model parameters of a support vector machine, which means the applicability of support vector machines in scenarios where interpretation is important for people may be limited when we want to understand why a particular prediction was made. As a reminder, there are three main parameters that control model complexity for kernelized SVMs. First, there's the kernel type, which defaults to RBF for radial basis function, but several other common types are available in scikit-learn's SVC module. Second, each kernel has one or more kernel-specific parameters that control aspects like the influence of training points according to their distance. In the case of the RBF kernel, SVM performance is very sensitive to the setting of the gamma parameter that controls the kernel width. Finally, for any support vector machine, the C regularization parameter operates as we've discussed before, and is typically tuned with the kernel parameter, such as gamma, for optimal performance. So far, we've seen a number of supervised learning methods, and when applying each of these methods, we followed a consistent series of steps. First, partitioning the dataset into training and test sets using the train-test split function, then calling the fit method on the training set to estimate the model, and finally applying the model by using the predict method to estimate a target value for the new data instances, or by using the score method to evaluate the trained model's performance on the test set. Let's remember that the reason we divided the original data into training and test sets was to use the test set as a way to estimate how well the model trained on the training data would generalize to new, previously unseen data. The test set represented data that had not been seen during training, but had the same general attributes as the original data set, or in more technical language, was drawn from the same underlying distribution as the training set. Cross-validation is a method that goes beyond evaluating a single model using a single train test split of the data by using multiple train test splits, each of which is used to train and evaluate a separate model. So why is this better than our original method of a single train test split? Well, you may have noticed, for example, by choosing different values for the random state seed parameter in the train test split function when you're working on some examples or assignments, that the accuracy score you get from running a classifier can vary quite a bit just by chance, depending on the specific samples that happen to end up in the training set. Cross-validation basically gives more stable and reliable estimates of how the classifier is likely to perform on average by running multiple different training test splits and then averaging the results, instead of relying entirely on a single particular training set. It's really important to understand how cross-validation is used in practice. The main scenario where you'll need cross-validation is when you have a particular classification task and you want to compare the accuracy of one type of model, let's say support vector machine, with a different model, let's say naive Bayes. In this scenario, to do that comparison well, you don't want to rely on the accuracy numbers from just a single train test split. Because it might be, just by chance, using that particular train test split, that the naive Bayes model happens to do better, when in reality it may actually be worse overall. So instead, you should compare the two approaches in a more reliable way by using cross-validation to create multiple train test splits, and then computing the overall mean evaluation metric across those folds. So for example, if you use 10-fold cross-validation, this will evaluate the two approaches using 10 different train test splits instead of a single one. And this will give you a more stable estimate of how each model is likely to do, compared to relying on just a single train test split. Once you've made your final decision on which modeling approach to use, and there's no more tuning left to be done, then you can train a final production classifier using all the data you have. One slightly confusing point here might be on how you use the multiple models that result from applying cross-validation. For example, 10-fold cross-validation will result in 10 trained models, each with its own set of estimated coefficients. When you apply cross-validation, you're simply computing an evaluation measure, like accuracy, for each of the 10 models, and then just taking the mean over those 10 evaluation numbers. That's it. With cross-validation, you're not producing a new hybrid model by merging together those 10 models in some way. Now, there are some special scenarios where you can do that, and that's a separate topic called model averaging, but we won't be going into that here. The bottom line is that if you want to compare two different model types, use k-fold cross-validation, and don't rely on just a single train test split when computing your evaluation numbers. It's also really important to understand the difference between using cross-validation for model evaluation versus using it for model tuning. If your task is to evaluate and compare different model types that have already been individually tuned and optimized, you use k-fold cross-validation with train test splits. But if your task is to tune a single model, such as when you want to find the best hyperparameters for a support vector machine, for example, this uses a slightly different setup, where instead of just a train test split, we divide our data into 3 slices called training, validation, and test splits. We'll cover how to use train, validate, test splits in the Model Selection Optimizing Classifiers lecture. Here's a graphical illustration of how cross-validation operates on the data. The most common type of cross-validation is k-fold cross-validation, most commonly with k set to 5 or 10. For example, to do 5-fold cross-validation, the original data set is partitioned into 5 parts of equal or close to equal size. Each of these parts is called a fold. Then a series of 5 models is trained, 1 per fold. The first model, Model 1, is trained using folds 2 through 5 as the training set, and evaluated using fold 1 as the test set. The second model, Model 2, is trained using folds 1, 3, 4, and 5 as the training set, and evaluated using fold 2 as the test set, and so on. When this process is done, we have 5 accuracy values, 1 per fold. In scikit-learn, you can use the cross-val-score function from the model selection module to do cross-validation. The parameters are first the model you want to evaluate, and then the data set, and then the corresponding ground truth target labels or values. By default, cross-val-score does 5-fold cross-validation. So it returns 5 accuracy scores, 1 for each of the 5 folds. If you want to change the number of folds, you can set the CV parameter. For example, CV equals 10 will perform 10-fold cross-validation. It's typical to then compute the mean of all the accuracy scores across the folds and report the mean cross-validation score as a measure of how accurate we can expect the model to be on average. One benefit of computing the accuracy of a model on multiple splits is that instead of a single split, it gives us potentially useful information about how sensitive the model is to the nature of the specific training set. So we can look at the distribution of these multiple scores across all the cross-validation folds to see how likely it is that, by chance, the model will perform very badly or very well on any new data set. So we can do a sort of worst case or best case performance estimate from these multiple scores. This extra information does come with extra cost. It does take more time and computation to do cross-validation. So for example, if we perform k-fold cross-validation and we don't compute the fold results in parallel, it'll take about k times as long to get the accuracy scores as it would with just one train test split. However, the gain in our knowledge of how the model is likely to perform on future data is usually well worth this cost. In the default cross-validation setup, to use, for example, 5 folds, the first 20% of the records are used as the first fold, the next 20% for the second fold, and so on. One problem with this is that the data might have been created in such a way that the records are sorted or at least show some bias in the ordering by class label. For example, if you look at our fruit data set, it happens that all the labels for classes 1 and 2, the apples and the mandarin oranges, come before classes 3 and 4 in the data file. So if we simply took the first 20% of records for fold 1, which would be used as the test set to evaluate model 1, it would evaluate the classifier only on class 1 and 2 examples and not at all on the other classes 3 and 4, which would greatly reduce the informativeness of the evaluation. So when you ask scikit-learn to do cross-validation for a classification task, it actually does instead what's called stratified k-fold cross-validation. The stratified cross-validation means that when splitting the data, the proportions of classes in each fold are made as close as possible to the actual proportion of the classes in the overall data set, as shown here. For regression, scikit-learn uses regular k-fold cross-validation, since the concept of preserving class proportions isn't something that's really relevant for everyday regression problems. At one extreme, we can do something called leave one out cross-validation, which is just k-fold cross-validation with k set to the number of data samples in the dataset. In other words, each fold consists of a single sample as the test set and the rest of the data as the training set. Of course, this uses even more computation, but for small data sets in particular, it can provide improved estimates because it gives the maximum possible amount of training data to a model, and that may help the performance of the model when the training sets are small. Sometimes we want to evaluate the effect that an important parameter of a model has on the cross-validation scores. The very useful function validation curve makes it easy to run this type of experiment. Like cross-val score, validation curve will do 5-fold cross-validation by default, but you can adjust this with the CV parameter as well. Unlike cross-val score, you can also specify a classifier, parameter name, and set of parameter values that you want to sweep across. So you first pass in the estimator object, or that is the classifier or regression object to use, followed by the dataset samples X and target values Y, the name of the parameter you want to sweep, and the array of parameter values that parameter should take on doing the sweep. Validation curve will return two two-dimensional arrays corresponding to evaluation on the training set and the test set. Each array has one row per parameter value in the sweep, and the number of columns is the number of cross-validation folds that are used. So for example, the code shown here will fit 4 models using a radial basis function support vector machine on different subsets of the data corresponding to the 4 different specified values of the kernel gamma parameter. So that will return 2 4x5 arrays, so 4 levels of gamma and 5 cross-validation folds containing the scores for the training and test sets. You can plot these results from validation curve as shown here to get an idea of how sensitive the performance of the model is to changes in the given parameter. The x-axis corresponds to values of the parameter, and the y-axis gives the evaluation score, for example, the accuracy of the classifier. Finally, as a reminder, cross-validation is used to evaluate a model and not learn or tune a new model. To do model tuning, we'll look at how to tune a model's parameters using something called grid search in a later lecture. Decision trees are a popular supervised learning method that, like many other learning methods we've seen, can be used for both regression and classification. Decision trees are easy to use and understand, and are often a good exploratory method if you're interested in getting a better idea about what the influential features are in your dataset. Basically, decision trees learn a series of explicit if-then rules on feature values that result in a decision that predicts the target value. Here's a simple example. Suppose we're playing a game where one person's thinking of one of several possible objects. So let's say an automobile, a bus, an airplane, a bird, an elephant, and a dog. A second person has to guess the identity of that thing by asking as few yes or no questions as possible, up to a limit of no more than, say, 10 questions. Suppose the first person secretly thinks of an automobile. So one of the first questions the second person might ask is it alive? Intuitively, we know that this type of broad question is much more informative and helps eliminate a larger set of possibilities early on, compared to asking a more specific question right away, like, does it have orange fur with black stripes? The more specific questions might be useful later, once we've narrowed the class of things down to particular animals or vehicles, for example. If we think of the property of being alive as a binary feature of an object, and the property of having orange fur with black stripes as another feature, we can say that the is-alive feature is more informative at an early stage of guessing, and thus would appear higher in our tree of questions. When the answer to the first question comes back as no, it's not alive, a second question might be, does it fly? When that answer comes back no, we can continue to narrow down the set of possible answers by asking more and more specific questions, such as, can it carry more than 10 people? In this way, any given object can be categorized as either matching the target object the first person is thinking of or not, according to its features, as determined by asking this series of yes or no questions. We can form these questions into a tree, with a node representing one question and the yes or no possible answers as the left and right branches from that node that connect the node to the next level of the tree, one question being answered at each level. At the bottom of the tree are nodes called leaf nodes that represent actual objects as the possible answers. For any object, there's a path from the root of the tree to that object that is determined by the answers to the specific yes or no questions at each level. For example, a dog is alive, cannot fly, and doesn't have a trunk. You can view this as a kind of simple decision tree for predicting the class of an object. We can generalize this idea of finding a set of rules that can learn to categorize an object into the correct category to many other classification tasks. For example, we're going to look at a classification task next that involves finding rules that can predict what species a particular flower is, based on measurements of certain parts of the flower. Rather than try to figure out these rules manually for every task, there are supervised algorithms that can learn them for us in a way that gets to an accurate decision quickly, which we'll look at now. Let's start by looking at a famous dataset in machine learning called the iris dataset. This dataset is included with scikit-learn in the Datasets module. Each instance in the dataset represents one of 3 different species of iris, a type of flower. There are 4 attributes, or features, for each instance that represent measurements of different parts of the flower. The sepal length in centimeters, the sepal width in centimeters, petal length in centimeters, and petal width in centimeters. The 3 species are called setosa, versicolor, and virginica. The dataset has measurements for 150 flowers with 50 examples of each species. The classification task is to predict which of the 3 species an instance is, given these measurements. Unlike our simple example involving yes or no questions, which were binary features of the object, The iris dataset's features are continuous values, so the rules to be learned will be of the form, for example, is petal length greater than 2.3 centimeters? Let's take a look at how a decision tree is built on this data. The goal when building a decision tree is to find the sequence of questions that has the best accuracy at classifying the data in the fewest steps. Looking at a decision tree, each decision splits the data into two branches based on some feature value being above or below a threshold. For example, whether the petal width is greater than 1.2 centimeters might be an example of a splitting rule. And that threshold is called a split point. An important concept is how informative a split of the data is. So intuitively, an informative split of the data is one that does an excellent job at separating one class from the others. An example of an informative split might be to put all instances of the flowers with petal length less than 2.35 centimeters into one bin and the rest in the other bin. This is an informative split because, at least for this training set, using that rule separates the Setosa class completely from the others and allows us to predict the Setosa class perfectly just based on this one measurement. A less informative split, like a rule like sepal width less than or equal to 3 centimeters, would not produce as clear a separation of one class from the others. So for the best split, the results should produce as homogeneous a set of classes as possible. There are a number of mathematical ways to compute the best split. One criterion that's widely used for decision trees is called information gain, for example. So to build a decision tree, the decision tree building algorithm starts by finding the feature that leads to the most informative split. For any given split of the data on a particular feature value, even for the best split, it's likely that some examples will still be incorrectly classified or need further splitting. In the iris dataset, if we look at all the flowers with petal length greater than 2.35 centimeters, for example, using that split leaves a pool of instances that are a combination of virginica and versicolor that still need to be distinguished further. So we can further improve the accuracy of the classification by continuing this process of finding the best split for the remaining subsets. With the iris dataset, we can further split into flowers that have petal length less than versus greater than 4.95 centimeters, for example. This second split is informative because the resulting subsets are more homogeneous. That is, the split did a good job at dividing virginica from versicolor based on this second split test. We can continue this process recursively until we're left with leaves in the decision tree that all have the same, or at least a predominant majority of a target value. Trees whose leaf nodes each have all the same target value are called pure, as opposed to mixed, where the leaf nodes are allowed to contain at least some mixture of the classes. To predict the class of a new instance, given its feature measurements, using the decision tree, we simply start at the root of the decision tree and take the decision at each level based on the appropriate feature measurement until we get to a leaf node. The prediction is then just the majority class of the instances in that leaf node. So for the iris data, for example, a flower that has a petal length of 3 centimeters, a petal width of 2 centimeters, and a sepal width of 2 centimeters would end up at this leaf node, whose instances are all of the virginica class. So the prediction would be virginica. Decision trees can also be used for regression using the same process of testing the feature values at each node and predicting the target value based on the contents of the leaf node. For regression, the leaf node prediction would be the mean value of the target values for the training points in that leaf. In scikit-learn, to build a decision tree, you import the decision tree classifier class from the sklearn tree module and fit it just as you would any classifier by creating the object and calling the fit method on the training data. This code first loads the iris dataset and then computes the training and test accuracy in predicting the three classes. Notice that the training data here is predicted perfectly with an accuracy of 1.0, while the test data is a little bit worse. This is an indication that the tree is likely overfitting. And in fact, this is a problem with building decision trees in general that keep adding rules until the leaf nodes are pure. Typically, such trees are overly complex and essentially memorize the training data. So when building decision trees, we need to use some additional strategy to prevent this overfitting. One strategy to prevent overfitting is to prevent the tree from becoming really detailed and complex by stopping its growth early. This is called pre-pruning. Another strategy is to build a complete tree with pure leaves, but then to prune back the tree into a simpler form. This is called post-pruning, or sometimes just pruning. The decision tree implementation in scikit-learn only implements pre-pruning. We can control tree complexity via pruning by limiting either the maximum depth of the tree, using the max depth parameter, or the maximum number of leaf nodes, using the max leaf nodes parameter. We can also set a threshold on the minimum number of instances that must be in a node to consider splitting it, and this would be using the min samples leaf parameter. We can see the effect of pre-pruning by setting max depth to 3 on the iris dataset. Now the accuracy on the training data is slightly worse, but the accuracy on the test data is slightly better. One great advantage of decision trees, at least when they're not too big, is that they're easy to interpret. Visualizing the entire tree can show you exactly how the decision tree is making its predictions. So let's take a look at an example. In the shared utilities Python code for this course, we've provided a function call named plot decision tree that takes the classifier object, the feature names, and the class names as input, and uses the GraphViz library to visualize the tree. It works by calling the export GraphViz function in the sklearn tree module to create a dot file, which is a text file description of the tree, and then using the GraphViz library to visualize the dot file, creating an image. Here's an example of how to call the plot decision tree function using the classifier we learned on the iris dataset. Here's the resulting plot for the unpruned iris dataset tree. The first line in a node indicates the decision rule being applied for that node. The second line indicates the total number of data instances for that node. The third line shows the class distribution among those instances, and the fourth line shows the majority class of that node's data instances. For example, in the root node, the initial pool of data has 37 Sentosa examples, 34 versicolor examples, and 41 virginica examples. After the first split into subsets that have petal length less than or equal to 2.35 on the left, and those that have petal length greater than 2.35 on the right, we have a leaf node on the left that consists entirely of the 37 Sentosa examples, and a decision node on the right that has 34 versicolor and 41 virginica examples. This node on the right then makes a second split based on petal length, using a threshold of 4.95 centimeters, and that creates two subsets of 36 samples on the left, containing 33 versicolor examples, and 39 samples on the right, 38 of which are virginica examples. We've used an option when plotting the decision tree to fill the nodes with colors that indicate the majority class of the data instances associated with that node. The intensity of the color indicates the strength of the majority count for that class. For larger trees that have, say, a depth of more than 5 or 10, instead of trying to analyze all the paths in the tree, it can be useful to see which paths most of the data takes. This can be done by looking for the largest samples values in the nodes. For example, if we follow the largest samples values down this tree, we can see that a significant set of 35 virginica examples are classified perfectly when their petal length is greater than 5.05 centimeters. Another way of analyzing the tree, instead of looking at the whole tree at once, is to do what's called a feature importance calculation. And this is one of the most useful and widely used types of summary analysis you can perform on a supervised learning model. Feature importance is typically a number between 0 and 1 that's assigned to an individual feature. It indicates how important that feature is to the overall prediction accuracy. A feature importance of 0 means that the feature is not used at all in the prediction. A feature importance of 1 means the feature perfectly predicts the target. Typically, feature importance numbers are always positive and they're normalized so that they sum to 1. In scikit-learn, feature importance values are stored as a list in an estimator property called feature underscore importances underscore. And note the underscore at the end of the name, which indicates it's a property of the object that's set as a result of fitting the model, and not, say, as a user-defined property. The shared utilities Python file contains a function called plot feature importances that you can import and use to visualize feature importance. It plots a horizontal bar chart with the features listed along the y-axis by name and feature importance along the x-axis. Here's the feature importance chart for the iris decision tree. In this example, for this particular train test split of the iris dataset, the petal length feature easily has the largest feature importance weight. We can confirm this by looking at the decision tree that this indeed corresponds to that feature's position at the top of the decision tree, showing that this first level, just using the petal length feature, does a good job splitting the training data into separate classes. Note that if a feature has a low feature importance value, that doesn't necessarily mean that the feature is not important for prediction. It simply means that the particular feature wasn't chosen at an early level of the tree. And this could be because the feature may be identical or highly correlated with another informative feature, and so doesn't provide any new additional signal for prediction. Feature importance values don't tell us which specific classes a feature might be especially predictive for, and they also don't indicate more complex relationships between features that may influence prediction. Even so, the feature importance values provide an easy-to-understand summary that can give useful insight about individual features in the learned model. Because feature importance can vary depending on the specific model learned for a particular train test split, for example, it's common when computing feature importance to use an average over multiple train test splits, for example, when performing cross-validation. Finally, let's apply decision trees to the breast cancer dataset that we've been using across multiple supervised learning algorithms. Here, we're controlling the model complexity by setting the max depth and min samples leaf parameters, and we've included the visualization of the resulting tree here, followed by a feature importance plot. As an exercise, try removing these two parameters to just use the default settings to see the effect on test set accuracy and the increase in overfitting that occurs. For this training set, the mean concave points feature gives the most informative initial split, followed by the worst area parameter. One of the major advantages of decision trees as a supervised learning method is that the decision rules are easily visualized and interpreted by people, including users without machine learning expertise. This makes decision trees a useful choice for getting an initial understanding of what some of the more important features are likely to be for a particular prediction task. Another advantage of decision trees is that you can use them without having to do feature preprocessing or normalization. Since each feature is processed independently and the splitting of the data doesn't depend on the absolute scale of the feature, the decision algorithm can operate on the original training data pretty much as is. So decision trees tend to work well with datasets that have a mixture of feature types, binary, categorical, or continuous, and with features that are on very different scales. One drawback of decision trees is that despite the use of pruning, they can still overfit on all or parts of the data and may not achieve the best generalization performance compared to other methods. One way to overcome that problem is to create what's called an ensemble of decision trees, which combines multiple decision trees to make a prediction. And we'll look at ensembles of decision trees in a following lecture. So to recap, scikit-learn enables you to control the model complexity of your decision trees with three key parameters. First, max depth controls the maximum depth, or the number of split points the decision can have, and is probably the most common parameter used to reduce tree complexity and thus reduce overfitting. The min samples leaf parameter is the threshold that controls what the minimum number of data instances has to be in a leaf to avoid splitting it further. This setting also reduces tree complexity. Finally, max leaf nodes limits the total number of nodes that are leaves of the tree. In effect, setting this parameter will indirectly influence the other two parameters and vice versa. So in practice, adjusting only one of these three is typically enough to control most overfitting, although even with the most optimized parameter settings, individual decision trees will still tend to overfit. In this video, I'm going to talk about what to do when you have categorical values for features or categorical values for labels. So a lot of the introductory machine learning examples that you might have seen assume that all the features are numeric, and it's a very common situation, though, to have features that are a category of something or a mixture of categorical and numerical features. So we're going to discuss in this video how to handle that particular situation. Okay, so let's take a specific example of what might be a categorical variable that you might see in a particular problem. Let's say we are looking at color. So there's a color feature in your data set, and the color can be one of several possible values. It can be red, yellow, green. It can be 30 different values depending on your application. But in general, the idea is that it's a category. So the category is part of a set of possible values. It's not a numerical value. And many predictors can't take a categorical input like this directly. So, for example, you can't take your color feature with its red, yellow, and green values and use it directly with, linear regression or logistic regression or support vector machines. Some methods can take categorical variables directly, like decision trees and decision tree-based predictors. But you may be faced with a situation where you have to figure out what you need to do to use categorical variables with a prediction method that can't deal with them directly. And by the way, some of these categories are encoded as numbers. Even though they're not numerical data, the categories might get mapped to numbers. So red might equal 1, yellow might equal 2, for example. So even if a column in your data set looks like it's a numerical feature, it may actually be a category feature encoded using numbers. So just be aware of that. So one very widely used solution to deal with categorical variables is called one-hot encoding. And what that does is it takes a single categorical value and turns it into a vector of binary values. The way the encoding works is you look at your categorical feature and you make a list of all the possible values that it could take. So in this example, I've pretended that there are only 3 possible color values, red, yellow, and green. So to get the one-hot encoding of the value red, we simply go through all the possible categories and we store 1 in the column that represents red and 0 for all the other categories. So in the one-hot encoding scenario, it's called a one-hot encoding because exactly one column is a 1, and that's the selected category, and the rest of the columns are 0. Let's take another example. Let's say we want to encode the value green for this row, and that's the 4th row. So you can see that in the one-hot encoding version of green, we have a 0 for red, a 0 for yellow, and a 1 for green. So very simple idea, and it's very widely used in statistics. For example, it's called a dummy encoding or a 1 of k encoding or an indicator variable. So that's how you convert categorical values into a vector of 0, 1 values that something like linear regression can actually handle now. Transforming categorical values into one-hot encodings is really easy in Python, whether you use pandas or scikit-learn. In pandas, we have this function called getDummies. And again, it's named that because one-hot encodings are called dummy variables in statistics. So getDummies can convert these categorical variables to dummy indicator variables. And you can see in this example, we created a list of values, A, B, C, A. And when we ask pandas to create the one-hot encoding for each of these, what it does first is it goes through and makes a list of all the possible values, so A, B, and C, and then for each of the entries, it will go through and mark for the entry A, it will make A equals 1 and then set the rest to 0 and so forth. So super easy to do in pandas. And in scikit-learn, it's also very easy. Now, there are two cases in scikit-learn to think about. One of them is if your categorical variable is a feature, in other words, it's in the X matrix. In that case, you would use sklearn preprocessing one-hot encoder to create the one-hot encoding vectors for each row for that feature. And you do that using the fit method, which will go through and look to find what are all the unique values in that feature column. And then once the one-hot encoder has been fit and has found all the possible unique values in that feature column, then you call transform to actually create the one-hot encoding vectors for that feature column. And those one-hot encoding vectors, by the way, by default are sparse. So this method produces a sparse matrix by default. You can change that if you want. You can set sparse equal to false. But by default, it's a sparse implementation. The second case in scikit-learn is where the thing that you're predicting, the label, is a categorical variable. So it might be that you want to convert a multi-class label, like suppose you're trying to predict a color. You might want to predict a binary label, so convert that multi-class problem into a series of binary problems. And to do that, you use label binarizer as the class that you apply that to. So it's similar to one-hot encoder in the way that you fit and transform. By default, in this case, actually, just a detail you should be aware of is that by default, that it actually produces a dense matrix in the current implementation of scikit-learn. So you can also, of course, turn that off and select sparse output if you need a sparse set of binary labels. But those are the two cases in scikit-learn where you want to use one-hot encoding, either as a feature or as a label. So here's a coding example that shows how fit and transform are used with the one-hot encoder object. So as usual in scikit-learn, the first step is to create the object. In this case, I'm also passing it the handle unknown option. And I'll talk about what that does in a minute. But right now, let's assume that we have some initial data which consists of 3 rows and 2 columns. So the first column is either male or female, and the second column is an integer, 1, 3, or 2. And when we call the fit method, scikit-learn's one-hot encoder object will analyze that, and it will find the unique values in the first column and the unique values in the second column. So the unique values in the first column would be female or male, and the unique values in the second column would be 1, 2, or 3. And we can see that when we look at the categories underscore variable that is set as a result of calling the fit method. We ask it, okay, what categories did you find in our data that we use for fit? And scikit-learn returns that in the first column, it found female and male as the categories. And in the second column, it found unique values of 1, 2, and 3. Now with this knowledge about the unique values in each category, we can do a transform, and we can ask scikit-learn to create a one-hot encoding vector for the first column, followed by the one-hot encoding vector for the second column. So if you have 2 successive columns that are categorical values, and you ask scikit-learn to do the transform, it will transform the first value into a one-hot encoding, and then concatenate the one-hot encoding vector for the second value. So let's ask it to transform a new little table which has female and the number 1 in the first row, and male and number 4 in the second row. And let's look at what the output is. So the one-hot encoding, so first it will create the one-hot encoding for female. And you'll notice that the categories that it found originally were female and male. So there are only 2 possible columns in the one-hot encoding, the female column and the male column. And you'll see that because we have the categorical value of female, it set correctly set the female column to 1 and the male column to 0. And you can see for the second row in this mini data set that male got mapped to the one hot encoding vector of 0, 1. Okay, so it's setting the male category to 1 in the second column. And you can see what it did for the one hot encoding of the numerical column. So it's treating the numerical column here as if it were a set of numbered classes. And when the second column's value is 1, that gets converted to a one hot encoding corresponding to this array. So it should create a one hot encoding vector of 1, 0, 0. And you can see indeed it does. But the second example is an interesting one. It's asking it to create a one hot encoding vector for a class, or an integer representing a class it's never seen before. You can see that there's no 4 in the set of unique values that it found for those numbers. So this is where the handle unknown setting comes in. So if you set handle unknown to ignore, what it will do is when it sees the value 4 and it tries to create a one hot encoding for a value that it never saw during the fit method, it will simply create, it'll put a 0. It'll put a 0 in that entry. Okay, so what it did here is it converted the number 4 to a one hot encoding vector that actually didn't have a 1, so it was all zeros. And that's what happens if you see a class in your test set, for example, that was never seen during training. Using the handle unknown option of ignore, it will create the one hot encoding vector that's all zeros. The other option for the handle unknown setting, you could also specify handle unknown equals error. And if you do that, then instead of silently creating an all zeros vector for an unknown class value, an unknown category value, it will actually create an error in the code, throw an error in the code, and halt the code. So, but that's the basic operation of one hot encoder. So finally, here's some rules to make sure that you apply this one hot encoding step properly. First, like many other types of transformations in scikit-learn, you always split the training and test sets first before fitting the one hot encoder object. You fit the one hot encoder object using the training data. You don't pass in the entire data set, including the test set. You must only do it after you split so that the one hot encoder doesn't get any knowledge of what is in the test set. And then once you fit the one hot encoder using the training data, you can use the transform function to apply this same one hot encoder you just fit to both the training data and the test data. So you need to make sure you use the same one hot encoder for training and test, and you need to make sure that you've only trained it using the training data. And that makes sure that dummy variables match across the training and test data and that all categories are represented. So a question that comes up is what happens if the test